In 1977, two spacecraft prepared to leave Earth on journeys unlike anything attempted before. They were called Voyager 1 and Voyager 2, although Voyager 2 would actually launch first. Inside control rooms at the Jet Propulsion Laboratory in California, engineers watched rows of instruments and glowing displays. Beyond those rooms waited four enormous planets that no spacecraft had ever examined closely. Jupiter was hundreds of millions of miles away. Saturn waited farther still. Beyond Saturn were Uranus and Neptune, worlds so distant that even powerful telescopes revealed little detail. Yet something unusual was happening in the outer solar system. The giant planets were slowly gathering into a rare geometric arrangement. It was an opportunity that would not return for roughly 175 years. And if engineers could build spacecraft capable of surviving the journey, gravity itself could carry them from one planet to another. The mission was supposed to explore distant worlds. Nobody yet knew that these machines would continue traveling for nearly half a century, eventually reaching the space between the stars. To understand how that journey became possible, however, the story begins long before launch. For most of human history, the outer planets were not destinations, they were wandering lights. People watched the night sky without knowing that worlds existed beyond Saturn. Uranus remained unnoticed as a planet until William Herschel recognized it in 1781. Neptune followed in 1846, discovered through a remarkable combination of mathematics and observation. Slowly, the known solar system expanded. By the 20th century, astronomers understood that Jupiter, Saturn, Uranus, and Neptune formed a distant family of giant planets. Yet understanding their existence was very different from visiting them. Through telescopes, Jupiter appeared striped and turbulent. Its great red spot suggested an atmosphere filled with enormous motions. Saturn seemed almost impossibly elegant. Its rings were visible even through modest instruments. Although their true complexity remained hidden across hundreds of millions of miles, Uranus appeared as a small bluish disk. Neptune was even more remote. Scientists could calculate their masses, orbital periods, and approximate compositions. They could study their light and follow their moons. But from Earth, countless questions remained unanswered. What were Jupiter's clouds really like? How were Saturn's rings constructed? What waited beneath the hazy atmosphere of Titan? Were Uranus and Neptune quiet frozen giants, or worlds with their own unexpected activity? For generations, there was no practical way to find out. Then rocketry changed the scale of astronomy. During the early decades of space exploration, robotic spacecraft began crossing distances that once belonged only to imagination. Missions reached the Moon, Venus, and Mars. The outer planets remained much harder. Distance was only one problem. A spacecraft traveling directly toward Neptune using the technology available in the 1960s might require an extremely long journey. It would need to remain functional through years of radiation, cold, and gradually weakening sunlight. Communication would become increasingly difficult. A radio command from Earth could take hours to arrive. A reply would require hours more. There would be no repair crew. No mechanic could replace a failed component. Every system would have to endure. Then astronomers and mission planners recognized an extraordinary opportunity. During the late 1970s, Jupiter, Saturn, Uranus, and Neptune would occupy positions allowing a spacecraft to visit several planets during one continuous journey. The planets were not forming a perfect straight line. That popular description simplifies what was really a useful arrangement of orbital positions. The important feature was timing. A spacecraft could approach Jupiter, fall into the planet's gravitational influence, and leave with its trajectory redirected toward Saturn. Saturn could then provide another gravitational encounter. With careful navigation, the process could continue outward. This technique became known as a gravity assist. Imagine, for a moment, approaching Jupiter aboard a silent robotic traveler. The planet grows from a bright point into a vast striped sphere. Its gravity begins bending your path before you arrive anywhere near its visible clouds. You fall toward the enormous world. Your speed increases. Then your curved trajectory carries you around Jupiter and outward again, with your motion altered relative to the Sun. Nothing needs to push you continuously across that encounter. Orbital mechanics does much of the work. The concept had been studied before Voyager, and gravity assists were already becoming part of planetary exploration. What made the late 1970s opportunity remarkable was the possibility of linking encounters across the outer solar system. Mission planners sometimes imagine an ambitious journey through several giant planets. It became associated with the idea of a grand tour, yet ambition had to survive budgets, engineering realities, and political decisions. A single enormous mission visiting every outer planet could become expensive and technically risky. Spacecraft would need unprecedented reliability. The original grand vision was therefore reshaped. NASA developed a more focused project initially centered on Jupiter and Saturn. The spacecraft would belong to the Mariner family of planetary missions, and the project was initially known as Mariner Jupiter-Saturn 1977. Its machines, however, would be built with possibilities extending beyond the simplest version of that description. Engineers understood something important. If the spacecraft survived Jupiter and Saturn, one of them might continue farther. That possibility influenced the machines they designed. Redundancy mattered. Long-lived electronics mattered. Power mattered enormously. Sunlight weakens dramatically with distance, making conventional solar power increasingly impractical for such a mission using the available technology. The spacecraft therefore needed another source of electricity. Radioisotope thermoelectric generators would convert heat from radioactive decay into electrical power. There were no moving turbines inside these generators. Heat flowed through thermoelectric materials, producing electricity while the radioactive source slowly weakened over decades. That gradual decline would eventually determine which instruments could remain alive. But in 1977, decades seemed almost abstract. First, the spacecraft had to survive launch. They had to cross the asteroid belt and endure Jupiter's dangerous radiation environment. Their computers had to function with capabilities tiny by modern standards. Their antennas had to remain pointed toward a planet that would become increasingly difficult to see from their perspective. Even the communication system required extraordinary patience. As distance increased, Voyager's radio signal would weaken. Earth would need enormous antennas and sensitive receivers to hear what eventually became a faint technological whisper across the solar system. Still, the mission was not purely mechanical. The spacecraft carried human curiosity in physical form. Their instruments could measure magnetic fields, charged particles, plasma, radiation, and planetary atmospheres. Cameras would return views of landscapes that no human eyes had previously seen. Every measurement would arrive as information transmitted across darkness. There was also something more unusual aboard them. A committee led by astronomer Carl Sagan helped prepare a message intended not for the mission controllers, nor even necessarily for humanity. Each Voyager would carry a gold-plated record. On it were images and sounds from Earth. There were greetings, natural sounds, scientific information, and selections of music. The likelihood of another civilization ever finding one of these records was extraordinarily small. Space between stars is simply too enormous. Yet the gesture mattered. The spacecraft were being designed for a scientific mission lasting years, while their physical bodies might survive for geological spans of time. Long after their power disappeared, the records could remain attached. For the engineers working before launch, however, such distant futures remained secondary. Their attention stayed on immediate problems. Components were tested. Systems were checked repeatedly. Trajectories were refined. A spacecraft intended to cross billions of kilometers could be endangered by something as ordinary as a faulty connection. There was another curious detail in the mission's naming. Voyager 2 would launch first. Its trajectory was slower and preserved the possibility of continuing toward Uranus and Neptune. Voyager 1 would launch later, but travel along a faster path toward Jupiter and Saturn. Eventually, it would overtake its sibling. So the numbers described mission trajectories and planned encounters rather than simple launch order. On August 20th, 1977, Voyager 2 stood aboard a Titan III-E Centaur rocket at Cape Canaveral in Florida. Around it was the familiar coastal atmosphere of the launch site: warm air, salt, machinery, and controlled anticipation. The spacecraft itself was small compared with the worlds it was intended to visit. Its main dish antenna measured about 3.7 meters across. Booms extended instruments away from the spacecraft body. its 3 radioisotope generators projected from another boom, providing the electrical heartbeat that would slowly diminish throughout the mission. When the rocket engines ignited, Voyager 2 began climbing through Earth's atmosphere. The departure was violent compared with everything that would follow. Within hours, the spacecraft entered the quiet rhythm that would define most of its existence, coasting, listening, measuring, waiting for commands from a shrinking Earth. 16 days later, on September 5th, Voyager 1 followed. 2 machines were now travelling outward. Behind them remained the only world where anyone knew they existed. Ahead waited Jupiter. Neither spacecraft had yet photographed its volcanic moon Io from close range. Nobody knew that Europa would become one of the most intriguing places in the search for potentially habitable environments beyond Earth. Nobody had seen Neptune's winds close enough to understand their astonishing speed. Even Uranus remained largely mysterious. The Voyagers were heading toward worlds that astronomers knew by outlines rather than intimate detail. There was an appealing uncertainty in that. Scientists had predictions, models, and expectations. Nature was under no obligation to respect them. As Earth slowly receded behind the spacecraft, radio signals continued crossing the widening distance. The mission had begun as an extraordinary planetary expedition. Its deeper identity had not yet emerged. Voyager would become something larger than a tour of the giant planets. It would become a measurement of how far functioning human technology could travel, how long careful engineering could survive, and how much the solar system could surprise the people who thought they understood it. But before any of that could happen, the machines themselves had to work, and building spacecraft expected to function years from Earth required engineers to prepare for failures they could predict, along with dangers they could not. That challenge would shape almost everything Voyager became by the early 1970s. Voyager existed less as a spacecraft than as a collection of difficult questions. How do you build a machine that must operate for years without repair? How do you protect electronics from Jupiter's radiation? How do you communicate across billions of kilometers? And how do you prepare for failures when a command from Earth might require hours simply to reach the spacecraft? At the Jet Propulsion Laboratory, these questions shaped almost every decision engineers made. The resulting spacecraft did not resemble the sleek machines imagined in science fiction. Voyager was an arrangement of antennas, booms, instruments, cables, electronics, and carefully protected systems. Its most recognizable feature was the large high-gain antenna. The white dish measured about 3.7 meters across and served as Voyager's principal connection with Earth. That connection would become increasingly precious. Near Earth, radio communication with a spacecraft could feel almost immediate. At Jupiter, a signal already required tens of minutes to cross the distance. At Neptune, communication became an exercise in patience. Much later, when Voyager entered interstellar space, commands would spend many hours traveling in one direction. The spacecraft therefore needed considerable independence. Voyager's computers were remarkably limited by modern standards, but comparing them directly with modern consumer electronics can be misleading. They were designed for reliability, specialization, and survival rather than convenience or raw computing speed. Several computer systems shared responsibilities. One handled spacecraft commands, another controlled orientation and attitude, a third helped manage scientific data. Together, they allowed Voyager to interpret instructions, control instruments, detect certain problems, and respond without waiting for immediate human intervention. This autonomy mattered because there would be moments when Earth could do nothing quickly. If Voyager detected a serious problem near Jupiter, the spacecraft might need to protect itself before controllers even knew something had happened. Engineers therefore built redundancy into critical systems whenever practical. Backup components waited quietly behind primary ones. Alternative communication modes were prepared. Software procedures were developed for situations nobody hoped to encounter. The philosophy was simple. Assume something will eventually fail, then make sure the mission does not necessarily fail with it. The environment beyond Earth made that philosophy essential. Space is often described as cold, but spacecraft temperature control is more complicated than simply surviving low temperatures. In sunlight, exposed surfaces can become warm. In shadow, temperatures can fall dramatically. Internal electronics also produce heat. Voyager needed thermal systems capable of keeping sensitive components within workable limits, while conditions changed throughout the journey. Then there was radiation. Jupiter presented the greatest immediate concern. The giant planet possesses an enormous magnetic field that traps energetic charged particles around it. A spacecraft passing through this environment can experience radiation capable of disrupting electronics and damaging instruments. Designers strengthened vulnerable components and prepared Voyager for an encounter that would test its engineering in ways impossible to reproduce perfectly on Earth. Yet radiation was only one threat. A spacecraft can also become lost without moving very far at all. Voyager needed to know where it was pointing. Its high-gain antenna had to remain oriented toward Earth during communications. Scientific instruments needed accurate pointing during observations. The spacecraft used sensors that could recognize the sun and selected bright stars. Among the most important reference stars was Canopus, one of the brightest stars in Earth's night sky. To a human observer, Canopus is simply a brilliant point of light. To Voyager, it could serve as a navigational reference in the darkness. Small thrusters adjusted the spacecraft's orientation. Their work was usually subtle. A brief firing could rotate Voyager until its antenna. Cameras or other instruments faced the required direction. Every maneuver consumed limited propellant. That meant orientation itself was a resource to be managed. Nothing aboard Voyager was truly unlimited. Electrical power was perhaps the clearest example. At Earth's distance from the Sun, solar panels are highly useful. At Jupiter, sunlight's far weaker. At Neptune, it is weaker still. Large solar arrays suitable for such a mission were not practical for Voyager's design and technology. Instead, each spacecraft carried 3 radioisotope thermoelectric generators. Inside them, plutonium-238 produced heat through radioactive decay. Thermocouples converted part of that heat directly into electricity. There were no spinning generators. No fuel was burned in the ordinary sense. The source simply became weaker with time. At launch, the generators provided hundreds of watts of electrical power. That was enough to operate the spacecraft and its scientific instruments. But the available supply would steadily decline. Engineers understood this from the beginning. They could calculate the radioactive decay. They could estimate how electrical components would age. What they could not know was whether the spacecraft would remain functional long enough for dwindling power to become a serious operational problem. Voyager had originally been developed around planetary encounters lasting years, not a functioning mission approaching half a century. Still, its construction quietly allowed longevity to become possible. The scientific payload was equally ambitious. Cameras could photograph planets, rings, and moons. Other instruments examined infrared and ultraviolet radiation. Magnetometers measured planetary and interplanetary magnetic fields. Particle detectors studied energetic particles moving through space. Plasma instruments sampled electrically charged material surrounding planets and flowing outward from the Sun. Radio experiments could investigate planetary atmospheres and rings by observing how transmitted signals changed while passing through or behind them, together. These instruments allowed Voyager to do something no telescope on Earth could accomplish. It could enter the environment being studied. Instead of merely observing Jupiter's magnetic field from afar, Voyager could move through it. Instead of guessing about particle populations around Saturn, it could measure them directly. Instead of seeing a moon as a tiny disk, cameras could reveal landscapes. The cameras themselves required careful planning. Digital images could not simply be transmitted instantly at enormous resolution. Voyager had limited data rates, limited storage, and limited communication opportunities. Observations had to be scheduled. Data sometimes had to be stored temporarily before transmission. Engineers and scientists constantly balanced scientific ambition against what the spacecraft could physically accomplish. Even a photograph involved orbital mechanics. Mission planners needed to know where Voyager would be, where the target would be, how illumination would fall across it, and when the spacecraft could transmit the resulting information. At planetary distances, photography became choreography. The machines also carried equipment that would later become unnecessary. Voyager's cameras were essential during the planetary encounters. Once the spacecraft had passed beyond the planets, however, there would be little nearby to photograph. Eventually, the imaging systems could be turned off. Other instruments would become more important as the spacecraft moved toward the outer heliosphere. This gradual transformation was not obvious at launch. Voyager had been designed primarily as a planetary explorer. Decades later, it would function more like a remote observatory sampling an environment no earlier spacecraft had reached. Before that transformation, every instrument needed to survive the launch from Earth. Engineers tested components through vibration, temperature changes, vacuum conditions, and electromagnetic environments. The tests could feel strangely harsh. A machine built for the silence of space first had to endure mechanical shaking designed to imitate the violence of a rocket launch. Small weaknesses mattered. A loose connection could become catastrophic. A component that worked perfectly at room temperature might behave differently after prolonged exposure to unusual thermal conditions. Testing, therefore, became a search for hidden fragility. There was also the problem of contamination. Planetary spacecraft had to be assembled carefully, both to protect sensitive equipment and to limit unwanted material traveling from Earth. Voyager was not intended to land on potentially habitable worlds, but cleanliness still mattered for engineering and scientific measurements. Then came one of the mission's most unusual additions. Mounted on the outside of each spacecraft was a circular record protected by an aluminum cover. The golden record was not necessary for navigation. It would not help Voyager survive Jupiter. It could not repair a computer. Scientifically, it was almost irrelevant to the immediate mission. Symbolically, it changed the spacecraft. The record contained sounds from Earth, spoken greetings, music, and encoded images intended to represent something of the planet that created Voyager. Its cover carried diagrams meant to communicate basic information about how the record could be played and where the spacecraft originated. The designers faced an almost impossible communication problem. How do you explain Earth without assuming a shared language? Mathematics and physical constants offered one approach. The record's creators used scientific references that they hoped an advanced finder might recognize. Of course, the chance of discovery was almost unimaginably small. Voyager was not aimed toward a known inhabited planet. Interstellar space contains enormous emptiness between stars. Even after traveling for tens of thousands of years, the spacecraft will merely pass within a few light years of other stars rather than conveniently arriving at them. The golden record was therefore less like a letter with an address, and more like a bottle released into a cosmic ocean. Its existence, nevertheless, reflected the peculiar scale of the mission. Human beings were constructing an object that might outlast nearly everything familiar to them. The spacecraft's electronics would eventually die. Its transmitters would become silent. Earth itself would change, yet in deep space, with little weathering or erosion. Much of Voyager's physical structure could endure for extraordinary lengths of time. That future was still remote when technicians prepared the spacecraft for launch. Their concerns were practical. Connections were checked, commands were tested, instrument covers were secured, the antenna system was examined. Every kilogram mattered because rockets could lift only so much mass onto the required trajectory. Every watt mattered because electrical power was finite. Every gram of propellant mattered because attitude control might someday depend upon it. The spacecraft that emerged from these constraints was not invulnerable. It was something more useful. It was adaptable. That adaptability would eventually allow engineers to solve problems decades after Voyager's designers could reasonably have expected anyone to remain in contact with it. Some solutions would involve switching to backup equipment. Others would require rewriting software or changing operating procedures. Still others would depend on understanding hardware designed by engineers who had long since retired. Voyager's longevity would eventually look almost miraculous from a distance. Up close, it was something less mysterious. It came from thousands of careful choices, redundant circuits, conservative engineering, patient testing, precise navigation, and teams willing to understand an aging machine as its condition changed. In 1977, however, none of that longevity was guaranteed. Two newly completed spacecraft sat at the beginning of their working lives. Their instruments had never seen Jupiter from nearby. Their antennas had never attempted to whisper across the outer solar system. Their computers had never faced the radiation belts waiting ahead. The machines had been built for the unknown. Now they needed to enter it, and beyond Earth. The first great test was already waiting in the distance, a planet so enormous that its magnetic environment alone could threaten the spacecraft before its cameras revealed what surrounded it. Jupiter was waiting. On August 20th, 1977, Voyager 2 waited beneath the Florida sky. Attached to a Titan IIIe Centaur rocket at Cape Canaveral, for years, the mission had existed inside laboratories, workshops, computer calculations, engineering meetings, and carefully controlled tests. Now nearly everything depended upon a few violent minutes. The spacecraft itself was delicate compared with the enormous launch vehicle surrounding it. Its instruments had been built to measure faint magnetic fields, distant radiation, and subtle changes in planetary atmospheres. First, they had to survive a rocket. When the engines ignited, the quiet machine disappeared inside vibration and thunder. The launch vehicle climbed above the Atlantic coast, carrying Voyager through the thick lower atmosphere. Forces pressed through its structure while guidance systems continuously adjusted the rocket's trajectory. Then the atmosphere began thinning. Stages separated. Engines completed their work. Eventually, Voyager 2 was released onto a path leading away from Earth. For the first time, the spacecraft was travelling independently through interplanetary space. There was no dramatic sensation of crossing a boundary. Earth simply began to recede. The blue planet remained enormous at first, accompanied by the moon and surrounded by darkness. Then distance slowly changed the view. Within days, Earth became another astronomical object behind the spacecraft. Voyager 2 had launched first because its planned trajectory was slower. This route preserved the possibility of continuing beyond Saturn toward Uranus and Neptune. That future remained uncertain. Officially, Jupiter and Saturn were the immediate objectives. Everything beyond them depended upon survival, funding, spacecraft health, and decisions that would not need to be made for years. Then, on September 5th, Voyager 1 launched. Its faster trajectory meant it would reach Jupiter before Voyager 2, despite leaving Earth 16 days later. The naming therefore reflected planned mission geometry rather than launch sequence. Soon, two nearly identical spacecraft were moving outward along different paths. Their departure created an unusual situation for controllers. There were now two distant machines requiring navigation, communication, scientific planning, and constant attention. Neither could simply be aimed toward Jupiter and forgotten. Interplanetary navigation demanded extraordinary precision. The planets were moving continuously around the Sun. Jupiter would not wait at a fixed destination. Mission planners needed Voyager to arrive at the place where Jupiter would be months later, while also approaching at the correct angle for the gravitational encounter that followed. A small error early in the journey could become enormous across hundreds of millions of kilometers. Engineers therefore performed trajectory correction maneuvers. Voyager's thrusters fired for carefully calculated periods, gently altering its path. The changes could appear insignificant, yet in spaceflight, tiny corrections made early enough can determine whether a spacecraft passes near a moon or misses it by thousands of kilometers. Navigation teams used radio signals to estimate the spacecraft's position and velocity. They measured how signals changed as Voyager moved relative to Earth. Stars provided additional orientation references aboard the spacecraft itself. Everything depended upon knowing where a machine was inside an almost featureless expanse. For the people following Voyager from Earth, the early cruise period could seem quieter than launch. There were no giant planets filling the cameras yet. There were no volcanic moons. No intricate rings had appeared. Mostly there was distance. But even the apparently empty space between Earth and Jupiter contained things worth measuring. Voyager's instruments sampled the solar wind, the continuous stream of charged particles flowing outward from the Sun. Magnetometers studied the magnetic environment. Particle detectors watched energetic material passing through interplanetary space. The spacecraft was already becoming a moving laboratory. You can imagine the journey from Voyager's perspective. Although the spacecraft itself could feel nothing. Behind it, the Sun remained brilliant. Around it, space offered almost no sound at all. There was no wind moving across the antenna dish. No engine continuously pushed the spacecraft forward. After the launch vehicle and occasional correction maneuvers had done their work, Voyager mostly coasted. Newtonian motion carried it onward. Days became weeks. Weeks became months. The distance from Earth increased almost invisibly. That quiet movement concealed enormous speed. Voyager travelled many kilometers every second relative to the Sun. Yet the scale of the solar system made progress feel slow. Jupiter remained far ahead. Meanwhile, the radio link with Earth became weaker. Voyager transmitted information using remarkably modest power compared with terrestrial broadcasting systems. Its high-gain antenna concentrated radio energy toward Earth, while enormous ground antennas listened for the faint returning signal. This network was part of NASA's Deep Space Network. Stations positioned around Earth allowed communication with distant spacecraft as the planet rotated. Facilities in California, Spain, and Australia provided broad coverage of the sky. The arrangement was elegant. As Earth turned and one station lost contact with a spacecraft, another could eventually take over. The antennas themselves became among Voyager's most important invisible companions. Without them, the spacecraft could make discoveries that nobody on Earth would ever receive. Communication involved more than simply listening. Commands travelled outward, telemetry travelled home. Scientific observations arrived as encoded data. Engineers examined information describing temperatures, voltages, instrument states, spacecraft orientation, and countless other details. A distant spacecraft could not explain its problems in ordinary language. It could only provide measurements. Controllers learned to interpret those measurements almost like physicians reading the vital signs of a patient they could never physically examine. There was a significant difference. Their patient was rapidly becoming unreachable. Every day made physical intervention more impossible. By design, there would never be a rescue mission. If something failed, the solution had to exist within the spacecraft already, or within the ability of engineers to change how surviving hardware behaved. This reality encouraged caution. Commands were checked carefully before transmission. An incorrect instruction could create consequences far from Earth. During cruise, teams also prepared for the coming encounters. Jupiter was not simply a large target. It was an entire system. The planet possessed many moons, a powerful magnetic field, an enormous atmosphere, and an environment filled with energetic particles. Scientists wanted observations of specific features at specific times. Camera sequences had to be planned around changing geometry. A moon might pass behind Jupiter. Another might cast a shadow across the cloud tops. A particular atmospheric feature might rotate into view. Voyager would move through the system quickly. There would be no opportunity to stop. The spacecraft could not enter orbit around Jupiter. Instead, it would fly past the planet, gathering observations during a relatively brief encounter before gravity sent it onward. Years of preparation would therefore concentrate into days. This made timing precious. Scientists competed gently, and sometimes not so gently, for spacecraft resources. Different instrument teams wanted observations. Navigation requirements needed priority at critical moments. Communication bandwidth remained finite. Power remained limited. The spacecraft could not satisfy every request simultaneously. Mission planning became an exercise in scientific compromise. There was another source of uncertainty. Jupiter's radiation environment was dangerous enough that nobody could know exactly how Voyager would behave during the closest portions of the encounter. Previous spacecraft had visited Jupiter. Pioneer 10 reached the planet in 1973, followed by Pioneer 11 in 1974. Their measurements gave Voyager planners invaluable information about Jupiter's environment. They also confirmed that the radiation belts were severe. Voyager would carry more sophisticated instruments and cameras into that region. Protection helped, but radiation can behave in troublesome ways around electronics. Energetic particles can interfere with circuits. They can create false signals. They can gradually damage components. Engineers could test systems on Earth, but no laboratory simulation could perfectly reproduce every condition encountered during a real planetary flyby. Jupiter would provide the final examination. As Voyager crossed the space between the planets, another small but memorable observation arrived. In September 1977, Voyager 1 photographed Earth and the Moon together. The image was not scientifically revolutionary, yet it offered a perspective rarely available at the time. Earth and its natural satellite appeared together against darkness, seen from beyond the immediate neighbourhood of both worlds. It was an early hint of a theme that would return much later. Voyager's cameras were designed primarily to look outward. Sometimes, however, looking backward changed the meaning of the journey. The spacecraft continued away. Earth became smaller. Radio travel time increased. The sun's gravitational influence remained dominant, but the familiar scale of human experience had already disappeared. There were no coastlines below Voyager now. No day and night in the ordinary terrestrial sense, only changing angles, measured distances, instrument readings, and the steady approach toward Jupiter. During this period, scientists continued refining what they expected to find. Jupiter's 4 largest moons had been known since Galileo observed them in 1610. Io, Europa, Ganymede, and Callisto were familiar names in astronomy. Yet through Earth-based telescopes, their surfaces remained poorly understood. Researchers could estimate their sizes and study some physical properties. Detailed landscapes were another matter. Many expected ancient, heavily cratered terrain similar in broad character to other small bodies already photographed. That was reasonable. Far from the Sun, these moons occupied a region commonly imagined as cold and geologically quiet. The assumption would not survive Voyager. Jupiter itself also contained unanswered questions. Its great red spot had been observed for centuries, but close imaging could reveal its structure and surrounding atmospheric motions in unprecedented detail. Bands of clouds stretched around the planet. Smaller storms appeared within them. The atmosphere seemed restless even from Earth. Voyager would watch it from close range. By late 1978 and early 1979, Jupiter was becoming more than a bright destination. It was becoming a visible world. Voyager 1's cameras began returning increasingly detailed images as the spacecraft approached. The planet grew larger frame by frame, bands separated into complicated currents. Cloud structures emerged. Moons that had once been points of light began showing surfaces. The encounter was approaching rapidly. Inside mission control, the rhythm changed. Years of engineering and months of crews were converging on a short period when the spacecraft would pass through one of the most complex environments in the solar system. The first major planetary test was about to begin. Scientists expected discoveries. They expected better photographs. They expected measurements that would improve existing models. What they didn't expect was for one small moon to overturn a comfortable assumption about the outer solar system. As Voyager moved toward Jupiter, Io waited inside the giant planet's powerful gravitational grip. Its surface looked strange. Then the images revealed something rising above it. The supposedly frozen moon was not dead at all. In January 1979, Voyager 1 was still millions of kilometers from Jupiter when the planet began transforming before its cameras. From Earth, Jupiter had always appeared majestic but distant, even through powerful telescopes. Its atmosphere was compressed into coloured bands, dark belts, bright zones, and the famous Great Red Spot. Voyager changed the scale completely. As the spacecraft approached, the broad stripes separated into twisting currents, turbulent boundaries, smaller storms, and complicated structures that seemed to move within one another. Jupiter was not simply striped, it was restless. The planet was more than 11 times wider than Earth, and contained more mass than every other planet combined. Yet there was no solid surface waiting beneath Voyager. The visible world consisted primarily of atmosphere, with clouds floating above increasingly compressed layers of hydrogen and helium. The deeper Voyager looked, the stranger the giant became. Mission controllers watched the approaching encounter from Earth, while signals crossed an enormous gulf between spacecraft and planet. By early March, Voyager 1 was close enough for the most intensive observations to begin. The spacecraft could not linger. It was moving through Jupiter's system at high speed, following a carefully designed trajectory that would eventually redirect it towards Saturn. Every hour mattered. Cameras photographed the planet repeatedly, allowing scientists to watch atmospheric structures change rather than seeing them only as isolated images. The Great Red Spot became especially compelling. It was already ancient by human standards. Astronomers had observed a large reddish feature in Jupiter's atmosphere for centuries, although connecting every historical observation to the modern storm remains uncertain. Voyager could finally examine its internal motion in detail. The images revealed an enormous rotating atmospheric system surrounded by turbulent currents. Smaller storms moved nearby. Clouds stretched, folded, and interacted along the boundaries between Jupiter's bands. The atmosphere looked almost fluid because, of course, it was. There were no continents interrupting these global currents. No mountain ranges redirected winds. No solid landscape anchored the weather beneath them. Instead, atmospheric motion could organize itself on scales difficult to reproduce on Earth. Scientists assembled sequences of Voyager photographs into moving views, Suddenly Jupiter's atmosphere could be watched. Cloud features circulated, storms rotated, bands slid past one another. For people accustomed to textbook images of the static planet, the effect was quietly revolutionary. Jupiter had become weather. The colours themselves required careful interpretation. Voyager's cameras recorded images through different filters, allowing scientists to construct colour views and study atmospheric features at selected wavelengths. The resulting pictures became some of the most recognisable images of planetary exploration. Yet the mission was doing far more than photography. Voyager's instruments entered Jupiter's enormous magnetic environment. The planet possesses the strongest planetary magnetic field in the solar system. Its magnetosphere forms a vast region shaped by the solar wind and filled with charged particles. For Voyager, entering that region meant entering danger. Radiation levels climbed. Energetic particles struck the spacecraft and affected its instruments. Some systems experienced temporary problems. Engineers watched carefully from Earth. The machine had been designed with Jupiter's radiation in mind. But calculations and laboratory tests were now confronting the real environment. Voyager continued functioning. Its magnetometers measured the field. Particle instruments sampled populations trapped within it. Radio observations added further information about Jupiter and its surroundings. The planet was revealing itself as more than an atmospheric giant. It controlled an enormous electromagnetic domain. Its moons existed inside that domain, and their relationship with Jupiter would soon become central to the encounter. Then Voyager found something that had escaped centuries of observation. Jupiter had a ring. It was faint. Nothing like Saturn's brilliant system was visible from ordinary Earth-based observations. Yet Voyager 1 detected a thin ring surrounding the giant planet. The discovery changed another familiar assumption. Planetary rings were no longer something belonging uniquely to Saturn. The outer solar system was beginning to suggest that ring systems might be a more general feature of giant planets. The ring was dark and difficult to observe. Its particles scattered sunlight differently from Saturn's bright icy material. Later studies would reveal a more complicated system of rings and dusty components associated with small inner moons. For Voyager's scientists, however, simply discovering the ring was enough to enlarge Jupiter's identity. There were surprises everywhere. The moons produced even greater ones. Jupiter's 4 large Galilean satellites had been known for nearly 4 centuries. Galileo had watched them move around Jupiter in 1610, helping demonstrate that not everything in the heavens revolved around Earth. Now Voyager was approaching the same moons from a distance Galileo could never have imagined. Callisto appeared heavily cratered. Its battered surface preserved evidence of impacts accumulated across immense stretches of time. Ganymede was different. It was enormous, larger than the planet Mercury, with terrain showing complicated patterns of ancient dark regions and brighter grooved areas. Europa looked stranger still. Its bright surface was crossed by long, dark lines. There were relatively few large impact craters. That scarcity suggested a surface that had been renewed sometime in its geological history. The exact nature of Europa would require later missions to explore more carefully. But Voyager had opened the question. Perhaps a small world far from the Sun did not need to remain permanently frozen and unchanged. Then there was Io. At first glance, Io looked almost unreal. Its surface contained yellow, orange, white, red, and dark regions unlike the cratered grey landscapes familiar from many earlier spacecraft images. Scientists searched for impact craters. They found remarkably few. Something was erasing them. One of the decisive moments came after Voyager 1 had passed Jupiter. Navigation engineer Linda Morabito was examining an image of Io taken for optical navigation purposes. Along the moon's edge, she noticed a strange protrusion. It seemed to rise above the surface. Further examination showed that Voyager had captured an enormous volcanic plume. Io was volcanically active. The discovery was extraordinary. Before Voyager, active volcanism had been directly known on Earth. Now it had been found on another world, and this world was smaller than Earth, cold in its location, and orbiting more than 5 times farther from the Sun than Earth does. Solar heat could not explain what Voyager was seeing. The answer came from gravity. Io travels around Jupiter in an orbit influenced by neighbouring moons, especially Europa and Ganymede. Their orbital relationships prevent Io's orbit from becoming perfectly circular. As Io moves around Jupiter, the changing gravitational pull flexes the Moon. Its interior is repeatedly squeezed and distorted. That flexing generates heat. The process is called tidal heating. Jupiter was effectively kneading its Moon through gravity. Suddenly, the outer solar system no longer looked like a collection of slowly freezing leftovers. Gravity itself could create internal heat. A Moon could remain geologically active without being close to the Sun. That realization would eventually influence scientific thinking about many other worlds. If tidal forces could heat Io enough to produce extraordinary volcanism, perhaps they could also warm the interiors of icy moons. Europa became particularly interesting. Its fractured surface hinted at a complicated history. Decades later, evidence would strongly support the existence of a global salty ocean beneath Europa's ice. Voyager had not discovered that ocean directly. What it had done was make such possibilities much harder to dismiss. The Jupiter system was becoming a miniature planetary system of its own. There was a giant central world. Moons occupied different environments around it. Radiation swept through the system. Gravity shaped their interiors. Small moons contributed material to rings. Io even supplied particles to Jupiter's magnetic environment through its volcanic activity. Everything was connected. Voyager 1 made its closest approach to Jupiter on March 5, 1979. A closest approach. It passed roughly 349,000 kilometers above Jupiter's cloud tops. The spacecraft moved through its programmed observations while Earth remained far away. Commands could not be improvised instantly. Much of the encounter depended upon sequences prepared beforehand. Cameras turned toward targets. Instruments collected measurements. Data flowed into spacecraft systems and then traveled home through radio. On Earth, the information arrived gradually. There was something almost peaceful about the delay. Voyager had already seen each scene before the people who built it could know what was there. A photograph existed aboard the spacecraft. Then its digital information crossed space. Only later did the image appear on screens in California. Human discovery traveled at the speed of light, yet still required patience. Voyager 1 left Jupiter with its trajectory altered by the planet's gravity. It was now headed towards Saturn. But Jupiter was not finished with Voyager. Voyager 2 was approaching behind its sibling. Its encounter came in July 1979. Scientists now knew where some of the surprises were hiding. They could use Voyager 2 to examine changes and investigate questions raised only months earlier. Io was especially valuable. Voyager 2 confirmed continuing volcanic activity and revealed that the Moon's surface could change over remarkably short geological intervals. The second spacecraft also expanded observations of Jupiter's atmosphere, magnetosphere, rings, and moons together. The twins transformed a distant planetary system into a place. Before them, Jupiter's moons had largely been astronomical objects. After Voyager, they possessed landscapes and geological histories. You had volcanoes. Europa had mysterious fractured plains. Ganymede displayed complex terrain. Callisto carried an ancient record of impacts. Even Jupiter itself had changed conceptually. Its great red spot was no longer merely an oval seen through telescopes. Its atmosphere was a moving ocean of gas filled with interacting structures. Its magnetic field created an environment extending far beyond the visible planet. Its faint ring showed that Saturn did not possess a monopoly on planetary rings, and its gravity could keep a small moon internally alive. The lesson was subtle but important. Distance did not mean simplicity. Cold did not necessarily mean geological death. A world that looked quiet through a telescope could become complicated when approached closely enough. Voyager had reached its first giant planet expecting to improve existing knowledge. Instead, Jupiter changed some of the questions. The spacecraft were now carrying those questions outward. Ahead waited Saturn, surrounded by rings far brighter and more intricate than Jupiter's newly discovered band. Voyager 1 would reach it first. There, another moon would influence the mission more than any other. Titan was wrapped in an atmosphere so thick that Voyager's cameras could not simply look through it. To approach that hidden world closely, Voyager 1 would have to sacrifice something enormous. It would have to leave the planetary road. By the time Voyager 2 left Jupiter in July 1979, the giant planet had already delivered more surprises than many scientists expected. Yet the deepest change came from its moons. For centuries, Io, Europa, Ganymede, and Callisto had appeared as 4 small lights circling Jupiter. Their movements could be measured precisely, but their surfaces remained distant and largely mysterious. Voyager transformed those lights into worlds. Each moon told a different geological story, even though all 4 occupied the same planetary system. The contrast was remarkable. Closest to Jupiter was a world roughly comparable in size to Earth's moon. Before Voyager, scientists could estimate its dimensions, orbit, and unusual coloration. Nobody had directly observed an active volcano beyond Earth. Then Voyager 1 returned the images that changed everything. Volcanic plumes rose hundreds of kilometers above Io's surface. Dark deposits surrounded active regions. Sulfur compounds helped create landscapes painted in yellows, reds, whites, and blacks. The moon seemed almost freshly made. Impact craters were difficult to find because volcanic activity repeatedly resurfaced the landscape. This immediately raised a question. Where was the energy coming from? It receives sunlight like every other body near Jupiter. But solar energy could not explain such intense geological activity. The answer was hidden in orbital mechanics. Io circles Jupiter in a gravitational relationship with Europa and Ganymede. For every orbit completed by Ganymede, Europa completes approximately 2, while Io completes approximately 4. This orbital resonance repeatedly tugs on the moons. Io's path remains slightly eccentric rather than becoming perfectly circular. As the moon moves closer to and farther from Jupiter, the gravitational force acting across its body changes. Io flexes. The deformation is small compared with the moon's overall diameter, yet it happens continuously. Rock inside Io is compressed and stretched. Friction and deformation produce enormous quantities of internal heat. Over geological time, this energy melts material and drives volcanism. The discovery introduced planetary scientists to a powerful idea. A world did not need sunlight or radioactive heating alone to remain active. Orbital relationships could provide energy. Gravity could warm worlds. That realization became even more intriguing when scientists looked outward to Europa. Europa appeared almost completely different from Io. Its surface was bright and icy. Long dark lines crossed it in complicated patterns, sometimes extending for thousands of kilometers. There were remarkably few large impact craters. A heavily cratered surface usually indicates great age because impacts accumulate over time. Europa's relative smoothness suggested that something had erased much of its ancient surface. Perhaps the ice had moved. Perhaps material had risen from below. Voyager could not provide a complete answer. Its images were limited compared with those returned by later missions. Still, Europa no longer looked like a simple frozen sphere. The possibility of internal activity became difficult to ignore. If tidal heating could melt rock inside Io, perhaps weaker heating could influence ice inside Europa. Water ice behaves like solid rock at sufficiently low temperatures, but under different pressure and temperature conditions it can deform. If enough internal heat existed, liquid water might survive beneath the frozen surface. Voyager did not prove the existence of Europa's subsurface ocean. That understanding developed through later observations and missions. But Voyager helped establish the geological puzzle that made the ocean hypothesis compelling. The little moon had become one of the most interesting places in the solar system. Farther from Jupiter waited Ganymede. It is the largest moon in the solar system, with a diameter exceeding that of Mercury. Ganymede is large enough that it might easily be imagined as a planet if it orbited the Sun independently. Voyager revealed a complicated surface. Some regions were dark and heavily cratered. Others were brighter and crossed by grooves, ridges, and long patterns of disrupted terrain. The difference suggested multiple periods of geological activity. Ganymede had not simply formed and remained unchanged. Its crust had been modified. Large areas appeared to have been stretched, fractured, and resurfaced during its distant past. Scientists debated exactly how these structures formed. The details remained subjects of investigation even decades later. Voyager had supplied the first broad geological map of a world whose history was far more complicated than expected. Later missions would add another extraordinary fact. Ganymede possesses its own intrinsic magnetic field, making it unique among known moons. Voyager itself did not establish that discovery conclusively, but its exploration created the foundation for the missions that followed. Then came Callisto. At first glance, Callisto seemed closer to what scientists might once have expected from an old outer solar system moon. Its surface was covered with craters, some overlapped others, creating a dense record of impacts stretching back through immense periods of time. Callisto appeared ancient, yet even here, Voyager found something memorable. A vast multi-ring structure called Valhalla spread across the surface. It was associated with an enormous ancient impact, instead of appearing simply as one circular crater. The event produced a complicated system of concentric rings extending across a huge region. Callisto offered a contrast with Europa. Europa's surface seemed relatively young. Callisto preserved a deep geological age. Two icy moons orbiting the same planet could evolve very differently. Distance from Jupiter was part of the reason. Tidal forces become weaker with increasing distance. Orbital relationships also differ. The moons therefore experienced different internal histories. Jupiter's system began to resemble a natural laboratory. Scientists could compare several large moons formed in the same general region, but shaped by different combinations of gravity, composition, heat, impacts, and time. Voyager also examined smaller moons. Amalthea, orbiting much closer to Jupiter, appeared irregular rather than spherical. Other small bodies were discovered through Voyager imagery. These moons helped scientists understand Jupiter's faint ring system. Tiny particles could be released from their surfaces when micrometeoroids struck them. The resulting dust helped to maintain portions of the rings. The entire Jovian system was interconnected. Moons influenced rings. Gravity heated interiors. Volcanoes supplied material to surrounding space. Jupiter's magnetic field captured charged particles. Io became especially important to this electromagnetic environment. Its volcanoes release enormous amounts of material. Atoms and molecules escape the moon and become ionized. These charged particles interact with Jupiter's magnetic field, creating a torus of plasma along Io's orbit. Voyager's instruments could study this relationship directly. A geological process occurring on a moon was affecting the magnetic environment of a giant planet. The boundaries between astronomy, geology, and plasma physics began to blur. That was one of Voyager's quiet achievements. The mission showed that planetary systems could not always be understood by studying objects separately. A moon's orbit could determine its internal temperature. Its volcanoes could influence a magnetosphere. Its neighbouring moons could maintain the orbital conditions that kept those volcanoes active. Everything participated in a larger system. There was also an important human dimension to these discoveries. Scientists had spent years preparing models of what Voyager might encounter. Those models were not foolish when they proved incomplete. They represented the best conclusions available from limited evidence. Before spacecraft exploration, distant moons were tiny objects observed through Earth's atmosphere. Researchers worked with brightness, spectra, orbital behavior, and indirect measurements. Voyager supplied a completely new category of evidence. Suddenly there were landscapes. The process illustrates how planetary science often advances. A theory is built from available observations. A new instrument reaches farther. The evidence changes. Then the theory changes with it. Io offered the clearest example. The expectation of a relatively inactive moon did not survive the first close images within a remarkably short period. Scientists recognized tidal heating as the mechanism driving its volcanism. An unexpected observation became a new framework. That framework later helped scientists think about worlds far beyond Jupiter. Saturn's moon, Enceladus, would eventually be found ejecting plumes of water-rich material from its south polar region. Tidal heating again became central to the explanation. Icy moons around other giant planets also attracted renewed interest. Even discussions about potentially habitable environments changed. For much of astronomy's history, habitability was closely associated with distance from the Sun. A planet needed to occupy a region where temperatures might permit liquid water at its surface. That idea remains important. Voyager helped reveal another possibility. Liquid environments might exist beneath ice, maintained partly by internal energy rather than direct sunlight. Europa eventually became the most famous example. Imagine standing above its surface. If such a journey were possible, Jupiter would dominate the sky. The ground would be water ice hardened by extreme cold. Dark fractures would stretch toward the horizon. Sunlight would be far weaker than on Earth, yet kilometers beneath that frozen landscape. There may be an ocean containing more liquid water than all Earth's oceans combined. Voyager could not see that hidden sea. It saw clues. Sometimes clues are enough to redirect generations of exploration. NASA later sent the Galileo spacecraft into orbit around Jupiter. Other missions studied the system remotely. Europa became the target of dedicated investigation. Ganymede would attract future exploration as well. The questions created during those brief Voyager flybys continued long after the spacecraft themselves had departed. This was perhaps the strangest aspect of the encounter. Voyager spent only a short time close to Jupiter. Its discoveries would occupy scientists for decades. Meanwhile, the spacecraft had no reason to wait. Orbital mechanics had already determined the next destination. Jupiter's gravity had bent the trajectories of both Voyagers and increased their heliocentric speeds in the required directions. Saturn was ahead. The journey between the giant planets would again require patience. Voyager 1 would arrive first in November 1980. Voyager 2 would follow in August 1981. From Earth, Saturn already seemed familiar because of its rings. No other planet possessed such an immediately recognizable appearance. Yet familiarity from a telescope could be deceptive. Voyager would discover thousands of structures within those rings. It would find shepherd moons helping shape them. It would observe a planet whose atmosphere contained enormous winds. And it would approach Titan, the only moon known to possess a thick atmosphere. Titan was the great mystery. Its atmosphere hid the surface beneath an orange haze. Scientists wanted Voyager 1 to pass close enough to investigate it carefully. Doing so required a particular trajectory around Saturn. That path carried a permanent consequence. Voyager 1 could visit Titan closely, or it could preserve a route toward more distant planets. It could not do both. The mission would choose Titan. One spacecraft would leave the planetary plane. The other would inherit the road to Uranus and Neptune. For the first time since launch, the twin journeys were about to separate in a fundamental way. In November 1980, Voyager 1 approached Saturn after travelling more than 3 years from Earth. Jupiter had already taught the mission an important lesson. The outer solar system was not a collection of simple, frozen worlds waiting quietly in darkness. It was active, complicated, and deeply interconnected. Now another enormous planet was growing ahead. Saturn had been known since antiquity because it can be seen without a telescope. For ancient observers, it was simply the slowest of the bright wandering lights moving against the stars. Its true appearance remained hidden until the invention of the telescope. When Galileo observed Saturn in 1610, his instrument could not clearly resolve the planet's rings. He described a strange world that seemed to possess companions or handles on either side. Later observers gradually understood the structure. By the 20th century, astronomers knew Saturn was surrounded by a broad system of rings composed largely of countless particles. But even the best Earth-based observations could reveal only part of their complexity. Voyager was about to enter that complexity as Saturn expanded through Voyager 1's cameras. The familiar rings separated into an astonishing number of structures. Broad, bright regions contained narrow bands. Dark gaps contained material of their own. Thin ringlets appeared where astronomers had expected smoother distributions. Some structures seemed braided. Others showed waves, sharp edges, and subtle variations in brightness. The rings were not static ornaments. They behaved like a dynamic system. Saturn's gravity controlled the overall architecture, but the planet's moons also shaped the material around them. Some small moons acted as shepherds. Their gravity helped confine narrow rings and maintain sharp boundaries. Prometheus and Pandora, for example, were associated with the narrow F ring. The ring itself proved particularly strange. Voyager image revealed clumps, kinks, and structures that appeared to change. Scientists had expected complexity. Saturn provided more than expected. The rings offered a natural laboratory for orbital mechanics. Each particle followed its own orbit around Saturn. Most were tiny compared with moons, ranging from dust-sized material to chunks of ice and larger bodies. Collectively, however, they formed structures spanning hundreds of thousands of kilometers. Small gravitational influences accumulated. Resonances with moons created gaps and waves. Particles collided gently and exchanged energy. The result was an enormous disk governed by gravity. For scientists studying how disks behave elsewhere in astronomy, Saturn became more than a beautiful planet. Some processes visible in its rings offered useful analogies for the disks of material surrounding young stars. The scales were different. The physics, however, sometimes rhymed. Voyager 1 made its closest approach to Saturn on November 12, 1980. The spacecraft passed roughly 124,000 kilometers above the planet's cloud tops. Its instruments studied Saturn's atmosphere, magnetic environment, rings, and moons, while the encounter unfolded at tremendous speed. Saturn itself appeared calmer than Jupiter at first glance. Its cloud patterns were less strongly coloured and often obscured by atmospheric haze. That visual softness concealed powerful motion. Voyager measured winds reaching extraordinary speeds near the equatorial region. The atmosphere was divided into bands, storms, and circulating structures. Although many were less visually obvious than Jupiter's, the spacecraft also investigated Saturn's magnetic field. Like Jupiter, Saturn possesses a large magnetosphere, yet its magnetic field presented an unusual feature. The magnetic axis appeared remarkably well aligned with the planet's rotational axis. For planetary scientists, that was puzzling. Many theories describing how planetary magnetic fields are generated involve motions inside electrically conducting fluids. A slight difference between rotational and magnetic axes is often expected. Saturn seemed inconveniently symmetrical. The puzzle would survive Voyager and continue through later missions. But the most important target for Voyager 1 was not Saturn itself, it was Titan. Titan had been discovered by Christian Huygens in 1655. By the 20th century, astronomers knew it possessed a substantial atmosphere. That alone made the Moon extraordinary. Most moons have either extremely thin atmospheres or almost none. Titan was different. Its atmosphere was denser at the surface than Earth's. Earth-based observations suggested methane was present, while nitrogen would eventually be recognized as the dominant atmospheric gas. But Titan's surface remained invisible. A thick orange haze covered the Moon. Scientists wanted to understand what lay beneath it. Voyager 1 was deliberately placed on a trajectory that would carry it close to Titan. This decision had been made before launch. It was scientifically compelling and strategically expensive. The spacecraft could not simply visit Titan and then continue toward Uranus. A close Titan encounter would significantly alter Voyager 1's trajectory. Gravity would bend the spacecraft upward, carrying it away from the relatively flat plane where most planets orbit the Sun. Once that happened, the road to Uranus and Neptune would be closed for Voyager 1. There was no practical way to turn around. The mission therefore faced a trade: Titan or the Grand Tour. Voyager une chose Titan. More precisely, the people designing its trajectory chose Titan because the Moon represented one of the most scientifically intriguing targets known in the outer solar system. Voyager 2 remained available as a possible traveller toward the remaining giant planets. That redundancy made the decision easier. Still, nothing guaranteed Voyager 2 would survive long enough to complete such a journey. On November 12th, Voyager 1 passed about 6,500 kilometers above Titan's surface. The cameras looked toward the Moon. They encountered haze. Titan appeared as a nearly featureless orange sphere for anyone hoping to see mountains, craters, or frozen plains. The images were frustrating. The atmosphere refused to reveal the ground, but instruments could learn from that atmosphere itself. Voyager observations showed that Titan's atmosphere was dominated by nitrogen. Methane was also present. The atmosphere extended far above the surface and contained layers of haze produced through complex chemistry. Sunlight and energetic particles break apart atmospheric molecules. Their fragments recombine into increasingly complicated carbon-bearing compounds. These products help create Titan's characteristic orange appearance. The Moon was cold, but chemically interesting. Its surface temperature was far below the freezing point of water. Water there would behave more like rock. Methane and other hydrocarbons, however, could participate in processes impossible under ordinary conditions on Earth. Voyager could not yet reveal the lakes and channels that later missions would discover. Still, Titan emerged as a world with a dense atmosphere and active organic chemistry. It was unlike any moon previously explored. Scientists debated what might exist beneath the haze. Some ideas were reasonable, others were speculative. The data were limited, and Voyager's cameras could not settle the matter. That uncertainty was important. Exploration does not always replace mystery with certainty. Sometimes it reveals that the mystery is larger than expected. Titan became exactly that kind of world. As Voyager 1 passed the moon, Titan's gravity pulled on the spacecraft. The effect was planned carefully. The trajectory bent. Voyager began moving above the main planetary plane. The choice was now irreversible. For Voyager 1, the era of planetary encounters was nearly over. It had visited Jupiter and Saturn. It had examined active Io-fractured Europa, enormous Ganymede, ancient Callisto, Saturn's rings, and hidden Titan. Now it was leaving the road that led to Uranus and Neptune. There was something quietly unusual about this moment. Voyager 1 remained healthy. Its instruments were functioning. Its cameras were capable of returning extraordinary images. Yet there were no more planets ahead of it. The spacecraft had not failed. Its trajectory had simply carried it into a different future. Voyager 2 still approached Saturn behind it. That spacecraft reached the planet in August 1981. Its encounter allowed scientists to revisit the ring system and examine changes that had occurred since Voyager 1. The second spacecraft studied Saturn's atmosphere, magnetosphere, moons, and rings from another trajectory. The comparisons were valuable. Features in the rings could change. Atmospheric structures evolved. Different viewing geometries revealed details missed during the first encounter. Voyager 2 also experienced difficulties. Its scan platform, which carried important imaging instruments, developed a problem after the Saturn encounter. The mechanism temporarily jammed. For a spacecraft expected to continue toward Uranus, the problem was serious. Without reliable pointing, future imaging could be badly compromised. Engineers investigated the behavior from Earth. They concluded that the platform had likely been overdriven, reducing lubrication and causing the mechanism to stick. Careful testing and altered operating procedures eventually restored useful movement. It was an early demonstration of something that would become central to Voyager's longevity. The spacecraft could age, hardware could behave unexpectedly, but engineers could sometimes adapt. By then, the possibility of continuing Voyager 2 toward Uranus was becoming real. Jupiter had worked. Saturn had worked. The spacecraft remained healthy enough to attempt something no machine had ever done. Uranus waited roughly another 5 years away. Neptune was farther still. NASA approved the extended journey. Voyager 2 would continue. The twins had now separated not merely by distance, but by purpose. Voyager 1 was climbing away from the planetary plane. Its future lay toward the outer heliosphere and, eventually, interstellar space. Voyager 2 remained closer to the plane where the planets travelled. Ahead of it stretched an almost empty darkness. There would be no planetary encounter in 1982, none in 1983, none in 1984. The spacecraft would simply travel. Its radioactive power supply would weaken gradually. Its instruments would continue operating. Controllers would continue listening. And somewhere ahead, Uranus would remain a pale blue-green point of light. For nearly 2 centuries, humans had known that distant planet existed. Nobody had seen its clouds closely. Nobody had flown past its moons. Nobody knew what Voyager would find there. The mission had already explored 2 giant planets. Now one spacecraft was being asked to cross a region so distant that sunlight itself would take hours to make the round trip between Earth and the machine. Voyager 2 was continuing alone. After November 1980, Voyager 1 was no longer travelling toward another planet. Titan had changed its path. The close encounter with Saturn's largest moon had bent the spacecraft upward, carrying it away from this broad plane where the major planets orbit the Sun. Behind it were Jupiter and Saturn. Ahead was something less visible. There were no giant worlds waiting to fill the cameras. No rings were scheduled to sweep across the field of view. No moon would suddenly reveal an unexpected landscape. Voyager 1 was entering the long outer journey. For the engineers on Earth, this created a peculiar transition. The spacecraft remained healthy. Its instruments still worked. Its radio transmitter continued sending data. Yet the mission that had originally justified its construction was essentially complete. Voyager 1 had explored Jupiter and Saturn successfully. By any reasonable standard, it had already accomplished an extraordinary scientific mission, but nobody wanted to switch it off. There was still useful science ahead. The space beyond Saturn was poorly explored, and Voyager possessed instruments capable of measuring magnetic fields, energetic particles, plasma, and cosmic rays. Instead of studying individual planets, it could begin studying the vast environment surrounding the Sun. This environment was invisible to human eyes. The Sun does more than provide light and heat. Its outer atmosphere continuously releases charged particles into space. This stream is called the solar wind. Near Earth, it can interact with Earth's magnetic field and contribute to auroras and space weather. Farther away, it continues flowing outward. The solar wind carries the Sun's magnetic field with it, creating an enormous region dominated by solar material and magnetic influence. This region is called the heliosphere. In the early 1980s, its distant boundaries were known mostly through models. Scientists understood that the solar wind could not expand forever without meeting the surrounding interstellar medium. Eventually, the outward-moving particles from the Sun would encounter material occupying the space between stars. Somewhere far beyond the planets, the solar wind would slow. Farther outward, the Sun's influence would give way to the interstellar environment. Exactly where these transitions occurred remained uncertain. Voyager 1 was now moving toward them. Nobody knew how long the journey would take. The distances were enormous, even travelling at roughly 17 kilometers each second relative to the Sun. Voyager needed years to cross regions that appeared almost empty on planetary maps. Speed in space can be deceptive. 17 kilometers per second is extraordinarily fast by human standards. At that speed, a journey between distant cities on Earth would last minutes. Yet the outer solar system is so large that Voyager could travel for decades without approaching another major world. The spacecraft did not experience this waiting. For the people following it, however, time became part of the mission. Teams changed. Scientists retired. New engineers joined. Computers on Earth became vastly more powerful, while Voyager's original electronics continued working with the same tiny capabilities they had possessed at launch. The spacecraft became a technological survivor from another era. In 1977, personal computers were only beginning to enter ordinary homes. There was no public internet. Mobile phones were rare experimental technologies. Voyager carried computers designed before many technologies that later generations would consider ordinary. Yet reliability mattered more than novelty. The spacecraft did not need modern graphics, enormous storage, or billions of calculations each second. It needed to point an antenna. It needed to operate instruments. It needed to accept commands. Most importantly, it needed to keep doing those things. As Voyager moved outward, engineers gradually changed how the mission operated. Power was declining. The plutonium-238 inside the radioisotope generators continued decaying, and the thermoelectric components also became less efficient. Year by year, less electrical power was available. The decline was predictable. Its consequences required choices. Not every heater could remain powered forever. Not every instrument would always be useful. Systems had to be prioritized. The spacecraft was becoming an exercise in careful subtraction. Something could be turned off to preserve something more important. A heater might be disabled. An instrument no longer useful for the extended mission could be retired. Electrical margins could be reclaimed 1 watt at a time. These decisions often involved uncertainty. Engineers knew recommended operating temperatures for components, but Voyager sometimes continued functioning below those expectations. The spacecraft repeatedly demonstrated that its hardware could tolerate conditions more severe than designers had originally planned. That did not make the decisions comfortable. Once a system was switched off, turning it back on might require precious power or introduce new risks. Every change had to be considered carefully. Communication also became more difficult. As Voyager receded, the radio signal reaching Earth weakened according to the geometry of spreading electromagnetic radiation. The transmitter did not become stronger to compensate. Earth had to become better at listening. The deep space network improved over time. Antennas were upgraded. Receivers became more sensitive. Signal processing techniques advanced. Multiple antennas could sometimes work together. The continuing Voyager mission therefore depended partly upon technology that did not exist when the spacecraft launched. The machines in space remained largely unchanged. Earth evolved around them. There was something quietly beautiful in that relationship. An old spacecraft transmitted with limited power. A changing planet built increasingly sophisticated systems to hear it. The conversation continued because both sides adapted differently. Voyager's increasing distance also created longer communication delays. A command could not produce an immediate response. Controllers sent instructions and waited. The spacecraft received them later. Telemetry confirming the result returned after another long crossing. Even routine operations demanded patience. Human instincts built around immediate feedback were not useful here. You could imagine sending a simple request into darkness, then walking away for hours before learning whether the distant machine had understood. That delay would continue growing. Voyager 1 was also leaving the region where cameras provided much scientific value. After Saturn, there were no nearby planets ahead. The imaging system remained functional, but most potential targets were distant points. Still, the cameras had one remarkable task left. The idea came from Carl Sagan and others who had long advocated turning Voyager's cameras backward. From far beyond the inner planets, the spacecraft could photograph the solar system it was leaving. There were technical concerns. Pointing the cameras near the sun could potentially damage them. Mission planners also had to consider whether the observation justified spacecraft resources. Eventually, the idea was approved. On February 14, 1990, Voyager 1 turned its cameras toward the planets behind it. By then, the spacecraft was roughly 6 billion kilometers from the sun. It took a series of images that became known collectively as the Solar System Family Portrait. Several planets were photographed from this extraordinary distance. Earth appeared in one frame. It was barely visible. The planet occupied less than a single pixel. A ray of scattered sunlight crossed the image, and within it rested a tiny point. That point was Earth. The photograph later became famous as the pale blue dot. Its scientific importance was modest compared with many Voyager measurements. Its cultural importance was enormous. Every human civilization had developed on that tiny world. Every ancient astronomer who studied the sky had stood there. Every engineer who built Voyager had lived there. The spacecraft had travelled billions of kilometres only to look backward and reduce its creator's entire world to a speck of light. There was no new scientific theory hidden in that pixel. The revelation was perspective. After completing the family portrait, Voyager 1's cameras were turned off. There was little reason to keep them operating. The decision saved power and reduced unnecessary spacecraft activity. The machine that had given humanity extraordinary images of Jupiter, Saturn, and their moons became effectively blind. But blindness did not mean silence. Voyager's remaining instruments continued sensing things cameras could never see. Magnetic fields passed through the spacecraft. Energetic particles struck detectors. Cosmic rays arrived from distant regions of the galaxy. The solar wind surrounded it. These measurements became increasingly valuable as Voyager travelled farther from the sun. The mission had transformed. Once scientists had waited for photographs of planets. Now they watched graphs. A sudden change in particle counts could indicate that Voyager had entered a new environment. A shift in magnetic measurements could reveal something about the structure of the heliosphere. The discoveries became less visually spectacular, but no less fundamental. There was also a growing uncertainty about distance. How large was the heliosphere? Models offered estimates, but the boundary was not a solid shell with a known radius. It changes with solar activity and interacts dynamically with the surrounding interstellar medium. Voyager might reach important transitions sooner than expected, or much later. Nobody could simply look ahead and see them. The spacecraft would have to detect the boundary by crossing it. Meanwhile, Voyager 2 was still pursuing a completely different destiny. While Voyager 1 moved toward the outer heliosphere, its sibling remained on the planetary road. Voyager 2 had passed Saturn in 1981 and was travelling toward Uranus. The distance between the spacecraft increased. Their stories now unfolded on separate timescales. Voyager 1 became a long-duration probe of the Sun's distant environment. Voyager 2 remained an explorer with two major worlds potentially ahead. The separation highlighted the extraordinary flexibility created by the original mission design. Two nearly identical machines had begun together. One sacrificed future planetary encounters for Titan. The other preserved the geometry needed to continue outward. For Voyager 1, there would never again be another close planetary flyby. That fact might have made the spacecraft seem finished. Instead, its longest scientific era was only beginning. Years passed, then decades. The sun became another bright star behind it. Although still overwhelmingly brighter than the surrounding stars from Voyager's position, solar power had never driven the spacecraft. So weakening sunlight did not determine its survival. Its radioactive generators continued providing electricity. The available power declined slowly. The signal continued reaching Earth, and Voyager continued outward. Eventually, its instruments would detect the solar wind beginning to change. The particles surrounding the spacecraft would slow. Cosmic rays from outside the heliosphere would become more noticeable. Something enormous was approaching, although nothing could be seen. Voyager 1 was nearing a frontier humanity had never crossed. But before that boundary could be understood, attention returned to the other spacecraft. Far behind its faster twin, Voyager 2 had spent years crossing an almost empty gulf. In January 1986, that waiting ended. A pale turquoise world began growing inside its cameras. Uranus was finally close. In August 1981, Voyager 2 left Saturn and entered one of the quietest periods of the entire mission. There would be no new planet waiting the following year. There would be no close encounter the year after that. Uranus was still billions of kilometers ahead, for more than 4 years. Voyager 2 would simply travel through the darkness between the giant planets. Its journey was now unique. Voyager 1 had already taken the close route past Titan, sending it permanently away from the planetary plane. Voyager 2 alone remained positioned to continue toward Uranus and perhaps Neptune. Nothing guaranteed either encounter. The spacecraft had already survived launch. Jupiter's radiation, years of interplanetary flight, and 2 giant planetary systems. Its original primary mission was essentially complete. Everything ahead depended upon an aging machine continuing to function. For the people controlling Voyager from Earth, the long cruise toward Uranus demanded a different kind of patience. Planetary encounters were intense. Years of preparation were compressed into days when cameras, spectrometers, particle detectors, and radio experiments gathered enormous amounts of information. Cruise was quieter. Commands still had to be transmitted. Spacecraft health still had to be monitored. Navigation still mattered. But much of the time, Voyager crossed an apparently empty region where nothing dramatic happened. That emptiness was deceptive. The spacecraft continued measuring the solar wind, energetic particles, and magnetic fields as it moved farther from the sun. The sun itself was changing from Voyager's perspective. At Uranus, sunlight is only a small fraction of its intensity near Earth. If you could somehow travel beside the spacecraft, the sun would still appear painfully bright. It would not look like an ordinary star, but its apparent disk would be much smaller, and its warmth would be almost meaningless against the surrounding cold. Voyager did not depend upon that sunlight for electricity. Its radioisotope generators continued producing power from radioactive decay. That design decision, made years before launch, was now allowing the spacecraft to operate where solar panels of comparable practical size would have been ineffective. The power supply was already weakening gradually. Engineers watched the margins carefully. There was another concern. Voyager 2's scan platform had developed trouble after Saturn. The platform carried cameras and several other instruments, allowing them to point towards scientific targets. During the Saturn encounter, the mechanism had been commanded through rapid movements. Afterward, it stopped moving properly, for a spacecraft headed toward 2 unexplored planets. The possibility of losing accurate instrument pointing was deeply troubling. There would be little value in carrying working cameras all the way to Uranus if they could not be aimed. Engineers began diagnosing the problem from more than 1 billion kilometers away. They could not inspect the mechanism. They could not touch it. There was no photograph of the damaged component available to them. They had telemetry. They had engineering records, and they had their understanding of how the machine had been built. Tests with comparable equipment on Earth helped reconstruct what might have happened. The problem appeared related to lubrication and excessive movement of the platform's gears. Controllers developed new procedures that limited how the mechanism was operated. Gradually, confidence returned. The scan platform could still be used. This episode quietly foreshadowed Voyager's future. As the spacecraft aged, engineers would increasingly become technological detectives. A strange voltage or unexpected temperature could become evidence. All diagrams would become essential. People would search through documentation created decades earlier. Sometimes retired engineers would be consulted because they remembered details no modern manual explained clearly. Voyager was beginning to acquire a history of its own. Meanwhile, the target ahead presented another challenge. Uranus receives its unusual appearance partly from methane in its atmosphere, which absorbs red wavelengths and contributes to the planet's blue-green color. From Earth, however, the planet offered frustratingly little visible detail. Its great distance made it difficult to study. Even its rotation had been challenging to determine precisely. Its moons were little more than points of light. Its rings had only been discovered in 1977, the same year Voyager launched. That discovery itself had been almost accidental. Astronomers observing Uranus from Earth had planned to watch the planet pass in front of a star. They expected the star's light to disappear when Uranus blocked it. Instead, the star dimmed several times before and after the main occultation. Something was orbiting the planet. Uranus had rings. The finding meant Voyager 2 would arrive at a system already known to be more complicated than earlier generations had imagined. But Uranus possessed an even stranger characteristic. The planet rotates almost on its side. Earth's rotational axis is tilted about 23 degrees relative to its orbital plane. Uranus has an axial tilt of roughly 98 degrees. Its poles therefore experience extraordinary seasonal illumination as the planet travels around the Sun, for part of its 84-year orbit. One polar region can face broadly toward the Sun while the opposite hemisphere remains in prolonged darkness. Why Uranus ended up this way remained uncertain. A giant collision early in solar system history was one possible explanation. More complicated gravitational interactions involving multiple impacts or satellite evolution have also been considered. Voyager would provide new constraints, but it could not reconstruct the planet's entire ancient history. This was a recurring theme in planetary exploration. A spacecraft could reveal what existed now. Understanding how it became that way was harder. As the encounter approached, scientists prepared for an additional difficulty. Voyager 2 would reach Uranus near the planet's southern summer solstice. One hemisphere was strongly illuminated, the other faced a long polar night. The geometry limited what cameras could observe. The spacecraft would also move through the system only once. There would be no second Voyager following months later. At Jupiter and Saturn, two spacecraft had provided complementary encounters. At Uranus, there would be only Voyager 2. Every observation became precious. The navigation challenge was equally demanding. Uranus was so distant that even tiny uncertainties in its moon's orbital positions mattered. Mission planners wanted close observations while keeping the spacecraft safe and preserving a trajectory toward Neptune. The encounter therefore had to serve two futures simultaneously. Voyager needed to explore Uranus. It also needed Uranus to send it onward. Gravity assists work only when geometry cooperates. Approaching on one side of a moving planet can alter a spacecraft's heliocentric velocity and direction differently from approaching on another. Mission designers carefully selected the path that would produce useful science, while maintaining the possibility of reaching Neptune. By late 1985, the long silence was ending. Uranus began growing in Voyager's images. At first, the planet looked almost disappointingly smooth. Jupiter displayed dramatic bands and enormous storms. Saturn had offered intricate rings and atmospheric structures. Uranus appeared comparatively featureless in visible light. Its atmosphere was wrapped in soft blue-green tones. A haze concealed much of the deeper cloud structure. There were atmospheric features. But the planet did not initially present the visual drama many had hoped to see. That apparent calm concealed something stranger. Voyager's instruments began investigating the magnetic environment. The results were extraordinary. Uranus possessed a magnetic field that was badly misaligned with the planet's rotation. Its magnetic axis was tilted by roughly 60 degrees from the rotational axis. Even more surprisingly, the magnetic field appeared significantly offset from the planet's center. The geometry was unlike the comparatively familiar configurations of Earth, Jupiter, or Saturn. As Uranus rotated, its magnetosphere behaved in a complicated way. The discovery suggested that the magnetic field might originate in conducting layers located differently inside the planet than the regions generating magnetic fields in Jupiter and Saturn. Voyager could measure the result. The exact interior mechanism remained uncertain. The spacecraft also examined Uranus's narrow dark rings. They were very different from Saturn's broad, bright icy structures. Several new rings and small moons were identified. Once again, the familiar picture of a planet expanded into an entire system. Then the cameras turned toward the moons. Aerial displayed valleys and faulted terrain that suggested geological activity in its past. Titania showed large fractures and canyons. Umbriel appeared darker and more heavily cratered. Oberon carried scars from a long history of impacts. Each moon offered evidence that the distant Uranian system had experienced more internal and geological complexity than a simple collection of frozen objects might suggest. But one small moon would dominate the encounter. Miranda was only about 470 kilometers across. Before Voyager, almost nothing about its surface was known. When the spacecraft returned close images, scientists found one of the strangest landscapes yet seen. Huge regions of radically different terrain appeared beside one another. There were enormous fault scarps. Ridges and grooves crossed the surface. Broad structures later called corona formed distinctive patterns unlike ordinary impact features. The moon looked almost assembled from mismatched pieces. Early descriptions sometimes suggested Miranda had been shattered and reassembled. That dramatic interpretation became popular because the surface looked so disordered. Later, geological thinking favoured more complex internal processes, including tectonic deformation and possible tidal heating. Rather than requiring complete catastrophic disruption, the uncertainty remains part of Miranda's appeal. Voyager showed the landscape clearly. It could not tell the entire story behind it. On January 24, 1986, Voyager 2 made its closest approach to Uranus. It passed roughly 81,500 kilometers above the visible cloud tops. Radio signals carrying observations then traveled for more than 2.5 hours before reaching Earth. The people waiting in California were watching events that had already happened. Voyager had crossed the Uranian system before anyone on Earth could see the encounter unfold through incoming data. There was no possibility of immediate intervention. The spacecraft executed stored commands autonomously. Cameras turned. Instruments measured. Data accumulated. Then the faint radio stream carried the results home. Uranus had changed from a pale telescopic disk into a complicated planetary system. Voyager discovered 10 previously unknown moons during the encounter. It examined rings, atmosphere, magnetic fields, and icy satellites. It revealed Miranda's extraordinary terrain. And then, almost as quickly as it had arrived, the spacecraft was leaving. There was no orbit insertion. No return. Uranus's gravity bent Voyager's trajectory and sent it toward the final giant planet. Neptune lay roughly 3 years and 7 months away. The distance was immense, but Voyager 2 had now survived for more than 8 years. Its cameras still worked. Its scan platform still moved. Its radio continued whispering toward Earth. The mission had reached a world no spacecraft had ever visited and departed with the possibility of doing it once more. Ahead was Neptune. It was darker there. Sunlight would be roughly 900 times weaker than at Earth. Scientists expected a cold world receiving very little solar energy. They did not expect the fastest planetary winds ever measured in the solar system. And they certainly did not expect Neptune's largest moon to reveal signs that its frozen surface was still active. Voyager 2 had one planetary encounter remaining. It would become its most distant. On January 24, 1986, Voyager 2 crossed the Uranian system and began moving toward a destination no spacecraft had ever reached. Neptune waited more than 3 years away. For the mission team, another long interplanetary crossing began. There would be no second opportunity if the spacecraft failed. Voyager 1 was already traveling far above the planetary plane, and no other mission was following Voyager 2 toward Neptune. Everything humanity would learn from this first close encounter depended upon one aging machine. By 1986, Voyager 2 had been operating for more than 8 years. Its original mission had been designed around Jupiter and Saturn. Uranus had already been an extraordinary extension. Neptune seemed almost like a mission borrowed from the future. The spacecraft continued outward through increasingly weak sunlight. At Neptune's average distance, the Sun provides only about 1/900th of the sunlight Earth receives. From there, the Sun would still appear much brighter than any other star, but the warmth familiar on Earth was effectively absent. Scientists naturally expected Neptune to be cold. That assumption was correct. What remained uncertain was how such a distant planet behaved. Neptune had entered human astronomy through one of the most celebrated predictions in scientific history. After Uranus was discovered in 1781, astronomers carefully measured its orbit. Over time, its motion did not perfectly match predictions based on the gravitational effects of the known planets. One possibility was that another unseen planet was disturbing it. During the 1840s, mathematicians independently calculated where such a planet might be found. In September 1846, observers at the Berlin Observatory located Neptune close to the predicted position. The discovery became a powerful demonstration of Newtonian gravitation. A world had effectively announced itself through its gravitational influence, before astronomers clearly identified it through a telescope. Yet discovery did not mean understanding. From Earth, Neptune remained a tiny bluish disk. Its atmosphere showed hints of activity, but fine details were extremely difficult to resolve. Its largest moon, Triton, had been discovered only weeks after Neptune itself. Much about Triton remained mysterious. By the late 1980s, scientists knew Neptune also possessed rings, although their appearance created confusion. Earth-based observations suggested that portions of the ring system might exist as incomplete arcs rather than continuous rings. That seemed dynamically strange. Ordinary orbital motion should spread material around the planet. Something had to be maintaining those concentrated structures. Voyager 2 could finally investigate. But reaching Neptune required more than simply surviving the journey. Navigation teams had to choose the final encounter geometry. There was no Uranus waiting beyond Neptune to provide another planetary destination. That gave mission planners unusual freedom. They could optimize the trajectory for science without preserving a path toward another giant planet. One target became especially important: Triton. The moon travels around Neptune in a retrograde orbit, meaning it moves opposite Neptune's rotation. That unusual behavior strongly suggests Triton did not form around Neptune in the same way as many regular moons. It was probably captured from elsewhere in the outer solar system. A close flyby could reveal what kind of world Neptune had captured. Mission planners selected a trajectory that would take Voyager close to Neptune and then onward toward Triton. This required passing over Neptune's northern regions before the spacecraft continued southward toward the moon. The geometry would eventually send Voyager 2 below the planetary plane. Like Voyager 1 after Titan, it would leave the road followed by the major planets. There would be no planetary encounter afterward. As 1989 approached, Neptune slowly grew in Voyager's cameras. Then something unexpected became obvious. The planet was not calm. Against its deep blue atmosphere appeared an enormous dark feature. Scientists called it the Great Dark Spot. Its appearance invited comparisons with Jupiter's Great Red Spot. Both were enormous atmospheric systems. But Neptune's storm existed in an environment receiving remarkably little solar energy. Voyager also observed bright clouds nearby. Some changed rapidly. Other atmospheric features moved around the planet. The supposedly quiet, distant giant possessed vigorous weather. Then came the winds. Voyager's observations revealed atmospheric motions reaching more than 2,000 kilometers per hour in some regions. These were among the fastest winds measured anywhere in the solar system. The discovery created an immediate puzzle. Why should Neptune possess such energetic weather? Jupiter receives much more sunlight. Earth's weather is driven largely by solar heating. Neptune, however, exists where sunlight is weak. Part of the answer lies inside the planet. Neptune emits substantially more energy than it receives from the sun. Heat escaping from its interior contributes to atmospheric activity. Exactly how that internal energy interacts with atmospheric circulation remains complicated. But Voyager made one thing clear. Distance from the sun did not imply meteorological stillness. The atmosphere itself was mostly hydrogen and helium, with methane contributing to absorption at red wavelengths. That methane helped produce Neptune's blue appearance. The exact richness of the color seen in processed Voyager images has required careful interpretation, because image processing can emphasize atmospheric contrasts. Scientifically, the important point was not simply Neptune's color, it was its activity. Clouds changed, storm systems moved, winds raced around the planet. Voyager had arrived at the edge of the known planetary system and found motion everywhere. Neptune's magnetic field provided another surprise. At Uranus, Voyager had discovered a magnetic field dramatically tilted and offset from the planet's center. Neptune showed something similarly unusual. Its magnetic axis was strongly tilted relative to the rotation axis, and the field was significantly offset from the planetary centre. Two neighbouring ice giants now displayed magnetic geometries unlike those of Jupiter and Saturn. This suggested that Uranus and Neptune might generate their magnetic fields in relatively shallow conducting layers rather than deep near their centres. The exact interiors remained hidden. Voyager could measure gravity, magnetic fields, atmospheric composition, and other properties. Scientists then had to infer what lay beneath the visible clouds. Neptune's rings also came into view. Voyager confirmed that the planet possessed several rings. Most importantly, the mysterious arcs observed from Earth were embedded within a continuous narrow ring. The material was not simply floating in disconnected segments. Certain regions were much denser and brighter than others. Small moons appeared to play an important role in maintaining this unusual structure through gravitational interactions. Once again, moons and rings were not independent systems. Gravity connected them. Voyager discovered previously unknown moons around Neptune as well. Among them was Proteus, an irregularly shaped body hundreds of kilometers across. It is large enough to approach the size where gravity might make a body spherical, yet it remains noticeably irregular. Other small moons occupied orbits close to the rings. Their presence helped scientists understand how the ring system could evolve and maintain structure. On August 25, 1989, Voyager 2 made its closest approach to Neptune. It passed roughly 5,000 kilometers above the planet's cloud tops. No spacecraft had ever come close to Neptune before. No spacecraft has returned since. For a brief period, humanity possessed a functioning machine moving through the immediate environment of the eighth planet. The spacecraft gathered observations according to sequences prepared long before the encounter. Earth was more than 4 light hours away. A command transmitted during the closest approach could not arrive until the event was already over. Mission controllers therefore watched delayed history. Voyager had already completed each maneuver by the time its telemetry described the event on Earth. The encounter belonged to the spacecraft first. Only later did it belong to humanity. Then Voyager moved beyond Neptune toward Triton. At roughly 2,700 kilometers across, Triton is Neptune's largest moon. Its surface temperature is extraordinarily low. Nitrogen, methane, and carbon monoxide can exist there as frozen materials. Scientists expected an ancient, cold surface. The images showed something more complicated. Triton's terrain contained relatively few large impact craters in the regions Voyager observed. That suggested portions of the surface were geologically young. There were broad plains and unusual textures. Some regions displayed terrain that later acquired descriptions such as cantaloupe terrain because of its distinctive appearance. Then Voyager observed dark streaks. Closer analysis revealed something remarkable. Plumes were rising above Triton's surface. Material was being ejected several kilometers upward before winds carried it horizontally through the thin atmosphere. These features were often described as geysers or cryovolcanic plumes. Their precise mechanism has remained a subject of scientific investigation. One leading explanation involves solar heating. Despite the weak sunlight, dark material beneath translucent nitrogen ice could absorb enough energy to warm subsurface nitrogen. Pressure might then build until gas and dark particles erupt through the surface. Another possibility involves internal processes. The available Voyager observations could not settle every detail. What mattered was the broader discovery. Triton was active. Once again, Voyager had reached a world expected to be frozen and quiet, only to find evidence of change. The pattern stretched back to Io. Distance from the Sun had repeatedly failed as a simple predictor of geological behavior. Gravity, internal heat, orbital history, volatile materials, and local conditions could create activity in places that appeared almost impossibly cold. Triton's retrograde orbit added another layer to the story, because it was probably captured by Neptune. The moon may once have travelled independently through the outer solar system. Its capture would have dramatically altered Neptune's original satellite system. Existing moons could have been scattered, destroyed, or forced into collisions. Triton itself would have experienced powerful tidal effects as its orbit gradually changed. The peaceful system Voyager observed might therefore preserve the aftermath of an ancient gravitational catastrophe. Scientists still debate details of that history. Voyager supplied clues rather than a complete reconstruction. after the Triton encounter. The planetary phase of Voyager 2's mission was over. There was no Pluto flyby ahead. The trajectory was wrong for it, and Pluto was never part of Voyager's route. Instead, Neptune's gravity and the Triton encounter geometry sent Voyager 2 southward relative to the planetary plane. Its cameras had completed their last close exploration of a major planetary system. From Jupiter to Neptune, one spacecraft had visited all 4 giant planets. No other spacecraft has repeated that journey. The Grand Tour, once reduced by practical constraints, had effectively been achieved by Voyager 2. The accomplishment was enormous, yet the spacecraft did not stop. There is no natural finish line in interplanetary space. After Neptune, Voyager simply continued moving. The Sun began shrinking still further behind it. The planets became distant points. Its cameras would eventually be turned off. Other instruments remained useful. Like Voyager 1, the spacecraft would now begin a different mission. The planets were behind both travelers. Ahead lay the outer heliosphere. For the first time, the twin Voyagers were heading toward a frontier no planetary photograph could reveal. In August 1989, Voyager 2 left Neptune behind and entered a region no spacecraft had ever explored so far from the Sun. Its planetary journey was over. For 12 years, the spacecraft had moved from one giant world to another, using gravity to cross distances that once seemed almost impossible. Jupiter had revealed volcanic Io and fractured Europa. Saturn had opened its intricate rings and hidden Titan. Uranus had shown a tilted world surrounded by strange moons. Neptune had revealed violent winds and an active Triton. Now there was no planet ahead. The cameras would never again watch another giant world grow from a distant point into a globe filling the frame. Yet Voyager 2 was still moving. Its trajectory carried it southward relative to the plane of the planets, while Voyager 1 travelled outward along a different path to the north. The twin spacecraft were separating across the solar system. Their destinations were no longer worlds. Their destination was the boundary of the Sun itself. That boundary could not be photographed. There was no wall waiting in the darkness. There was no line painted across space where the solar system ended. Instead, the transition existed through particles, magnetic fields, pressure, and plasma. To understand what the Voyagers were approaching, scientists had to reconsider what it meant to leave the solar system. There are several possible definitions. The planets orbit within the gravitational influence of the Sun, but solar gravity extends vastly farther than Neptune. Far beyond the known planets lies the distant population of icy bodies associated with the Oort cloud. If Voyager needed to escape every region where objects remained gravitationally bound to the Sun, its journey would take many thousands of years. The spacecraft were approaching a different frontier. They were moving toward the edge of the heliosphere. The Sun continuously releases the solar wind, a stream of electrically charged particles flowing outward through the planetary system. Near Earth, these particles move at hundreds of kilometers per second. They pass the planets and continue outward. As they travel farther, however, they eventually encounter resistance from the interstellar medium. The space between stars is not truly empty. It contains thinly distributed atoms, ions, dust, cosmic rays, and magnetic fields. The density is extraordinarily low compared with Earth's atmosphere. Still, across astronomical distances, this material matters. The solar wind pushes against it. The surrounding interstellar medium pushes back. Between them forms an enormous changing region around the Sun. Voyager was moving toward that interaction zone. Scientists expected several important transitions. The first major one was the termination shock. Despite its dramatic name, nothing would explode there. The solar wind travels outward faster than characteristic wave speeds within the plasma. At the termination shock, it slows abruptly as pressure from the surrounding environment becomes increasingly important. Beyond this lies the Helios Heath. Here, the solar wind continues outward more slowly, becoming compressed and disturbed. Farther still lies the heliopause. The heliopause marks the boundary where the outward pressure of solar plasma balances the surrounding interstellar medium. Beyond it, the spacecraft enters interstellar plasma. In the early years of the Voyager mission, nobody knew exactly where these boundaries would be found. Models provided estimates, but estimates depended upon assumptions about solar activity, interstellar conditions, magnetic fields, and the shape of the heliosphere. The Voyagers would eventually provide direct measurements. First, however, they had to survive long enough to get there. By the 1990s, the spacecraft were becoming old by engineering standards. Their radioisotope generators produced less electricity each year. Mechanical systems had accumulated years of use. Some instruments no longer served useful scientific purposes and were switched off. Others remained essential. Mission operations increasingly revolved around conserving power without sacrificing the instruments needed for heliospheric science. The cameras were among the systems eventually retired. Voyager 2 had completed its final planetary imaging at Neptune. There were no nearby worlds ahead requiring detailed photography. Keeping imaging systems active would consume resources without providing comparable scientific value. The mission therefore became less visual. For the public, this could make the Voyagers appear quieter. There were no spectacular new photographs appearing regularly. For heliophysicists, however, the spacecraft were moving toward their most unique scientific territory. Particle instruments could count energetic particles arriving from different directions. Magnetometers could examine the surrounding magnetic field. Plasma measurements could reveal properties of the solar wind. Plasma wave instruments could detect oscillations that helped scientists infer the density of surrounding charged material. The Voyagers were becoming probes of an invisible ocean. Earth remained connected through radio. That connection now depended more heavily than ever upon the deep space network. As distance increased, Voyager's signal became weaker. The spacecraft transmitted using power comparable to a small household light bulb. By the time that signal spread across billions of kilometers and reached Earth, it was extraordinarily faint. Large antennas collected what little energy arrived. Sensitive electronics separated the spacecraft's transmission from background noise. Modern signal processing extracted information from a whisper. Communication speed also declined. During planetary encounters, Voyager had transmitted images containing substantial quantities of data. In the distant cruise, the available data rate became much smaller. Fortunately, the remaining scientific instruments did not require the bandwidth of continuous imaging. Measurements could be encoded efficiently. A few numbers describing particles or magnetic fields could carry enormous scientific importance. The character of exploration had changed. A dramatic image could once reveal an unknown volcano. Now a change in a graph might reveal an unknown boundary. On Earth, the Voyager teams also changed. Some of the people who had designed the spacecraft retired. Others moved to different missions. A smaller group continued operating the aging probes. Knowledge had to be transferred between generations. This created an unusual engineering problem. Modern spacecraft teams normally work with systems built using relatively recent technologies. Voyager engineers were increasingly dealing with hardware and software designed in the early 1970s. Documentation became precious. Old engineering drawings were consulted. Archived notes could matter. Sometimes understanding a strange spacecraft behavior required reconstructing why a design decision had been made decades earlier. The people operating Voyager were becoming historians of their own machine. There was gentle irony in this. Voyager had been sent to investigate ancient worlds. Now the spacecraft itself had become an artifact. Yet it continued working. During the 1990s, Voyager 1 maintained its position as the more distant of the twins. Its faster trajectory carried it steadily outward. Voyager 2 followed along another direction. Scientists watched both because the heliosphere might not be symmetrical. The surrounding interstellar magnetic field, the sun's motion through the local interstellar environment, and variations in solar activity could distort its shape. Two spacecraft crossing different regions offered something far more valuable than one. They could compare boundaries. The heliosphere also changes with the solar cycle. Approximately every 11 years, the sun's magnetic activity rises and falls. Solar eruptions send disturbances outward. Those disturbances can travel through the heliosphere for months, far from Earth. Voyager could detect the echoes of events that had begun near the sun long before. The spacecraft were therefore not simply moving through a static bubble. They were travelling through a living extension of solar activity. One particularly useful phenomenon involved powerful solar eruptions. When major disturbances propagated outward, they could eventually compress plasma near Voyager. The spacecraft's plasma wave instrument could detect resulting oscillations. From their frequency, scientists could estimate electron density. This technique would later become essential for determining when Voyager 1 had entered interstellar plasma, but that discovery remained years away. First came the termination shock. By the early 2000s, Voyager 1 began detecting changes suggesting that this frontier was approaching. The intensity and direction of energetic particles shifted. The solar wind environment behaved differently. Scientists debated what the measurements meant. There was no single instrument aboard Voyager capable of flashing a message saying that a boundary had been crossed. The evidence had to be assembled. Different measurements did not always change simultaneously. Nature rarely arranges itself according to the neat diagrams drawn in textbooks. In December 2004, Voyager 1 crossed the termination shock at roughly 94 astronomical units from the Sun. 1 astronomical unit is approximately the average distance between Earth and the Sun. Voyager was therefore nearly 100 times farther from the Sun than Earth. The solar wind around it slowed dramatically. The spacecraft had entered the heliosheath. This was a major milestone. For the first time, a human-made object had directly sampled this distant region. Voyager 2 reached the termination shock later, in 2007. It crossed at a different distance, roughly 84 astronomical units. The difference was scientifically important. The heliosphere was not a perfectly spherical bubble centered neatly on the Sun. Its boundaries moved and changed. External pressure and solar activity influenced their positions. The two Voyagers were providing direct evidence of that complexity. For Voyager 2, the crossing offered an additional advantage. Its plasma instrument was still operating. Voyager 1's comparable instrument had stopped functioning decades earlier. Voyager 2 could therefore directly measure changes in the solar wind plasma during its passage. The twins were no longer identical scientific observers. Failures and operational choices had given each a different set of surviving abilities. Together, they remained more powerful scientifically than either alone. Beyond the termination shock, both spacecraft travelled through the heliosheath. The solar wind was slower there. Particles behaved differently. Magnetic fields became compressed. Scientists expected the heliopause somewhere ahead. Again, nobody knew precisely where. Years passed. Voyager 1 continued moving faster and remained farther from the Sun. Its measurements began showing increasingly unusual behavior. Particles originating inside the heliosphere decreased. High-energy cosmic rays associated with the galaxy increased. The spacecraft seemed to be approaching a region where the Sun's particle dominance was weakening. Then, in 2012, the changes became dramatic. Certain particles associated with the heliosphere suddenly dropped. Galactic cosmic rays increased. Something had happened. Yet one expected signature created confusion. Scientists had anticipated a significant change in magnetic field direction when Voyager crossed the heliopause. That change did not appear as clearly as expected. Had Voyager truly entered interstellar space, or had it reached another previously unknown layer inside the heliosphere? For months, researchers debated the evidence. The spacecraft had reached a frontier, but the frontier did not behave exactly as the models predicted. Then the Sun provided an unexpected way to answer the question. A powerful solar eruption sent a disturbance travelling outward through the solar system. More than a year later, that disturbance reached the region around Voyager 1. The spacecraft listened. The surrounding plasma began to oscillate. From those vibrations, scientists could calculate its density. The answer would finally reveal what kind of space surrounded Voyager. After 35 years of travel, the first human-made object was about to be recognized as an interstellar spacecraft. On August 25, 2012, Voyager 1 crossed a boundary that no human-made object had ever crossed before. There was no photograph of the moment. No camera could show a line separating the solar system from interstellar space. Nothing struck the spacecraft. No alarm sounded. Voyager simply continued moving while the particles surrounding it changed. At roughly 121 astronomical units from the Sun, the spacecraft passed through the heliopause and entered interstellar plasma. Humanity had sent a machine beyond the protective bubble created by the solar wind. Yet the mission team did not immediately know with certainty that the crossing had occurred. The evidence arrived gradually. For years, Voyager 1 had travelled through the heliosheath, where the solar wind had slowed after passing through the termination shock. Scientists expected the heliopause somewhere ahead. They also expected several measurements to change when the spacecraft crossed it. Some behaved almost exactly as predicted, others did not. During 2012, Voyager detected dramatic changes in energetic particles. Particles originating from within the heliosphere declined sharply. At almost the same time, galactic cosmic rays increased. These high-energy particles arrive from beyond the solar system, often produced by energetic processes elsewhere in the galaxy. Inside the heliosphere, the Sun's magnetic environment partially shields the inner solar system from some of them. Near the boundary, their abundance changed. The pattern seemed compelling. Voyager appeared to have crossed into interstellar space. But the magnetic field complicated the interpretation. Many models suggested its direction should change noticeably outside the heliopause. Voyager did not observe the dramatic rotation some researchers anticipated. Scientists hesitated. Perhaps Voyager had entered an unknown transition region. Perhaps the heliopause was more complicated than expected. Perhaps the spacecraft had not crossed it at all. This uncertainty was not a failure. It was exactly what happens when a spacecraft reaches a place never measured directly before. Models are built from available evidence. Then exploration tests them. Voyager had reached a region where the maps were theoretical. Nature was now correcting those maps. The decisive clue came from an instrument that did not require a functioning plasma detector. Voyager 1's dedicated plasma instrument had stopped working in 1980. That failure might have seemed disastrous for identifying the heliopause, because plasma density is one of the clearest ways to distinguish environments. Interstellar plasma was expected to be denser than the solar wind near the outer heliosphere. Fortunately, another instrument could measure density indirectly. Voyager carried a plasma wave system. It could detect oscillations in surrounding charged particles. Under suitable conditions, the frequency of these oscillations reveals the electron density of the plasma. The challenge was making the plasma oscillate strongly enough to measure. The Sun provided the disturbance. In March 2012, a series of powerful solar eruptions sent material and pressure disturbances outward. These events travelled far beyond the planets. They did not reach Voyager immediately. The heliosphere was far too large for that. More than a year later, the disturbance arrived in Voyager's neighbourhood. In April 2013, the plasma wave instrument detected characteristic oscillations. Scientists analysed their frequency. The inferred density was much higher than expected within the ordinary heliosheath. Voyager was surrounded by interstellar plasma. Researchers could then examine earlier measurements and identify another period of plasma oscillations. Those data allowed the crossing date to be traced backward. The best evidence indicated that Voyager 1 had entered interstellar space on August 25, 2012. The announcement came later. By then, the spacecraft had been travelling for 35 years. A mission originally built for encounters with Jupiter and Saturn had become the first direct probe of the environment between stars. The phrase interstellar space can create misleading images. Voyager had not left the Sun behind completely. It had not escaped the solar system under every possible definition. The Sun's gravity still dominated its trajectory. The distant Oort cloud, if current models are broadly correct, extends vastly farther outward. Voyager will require centuries even to approach its inner regions and tens of thousands of years to travel beyond the full domain of distant cometary bodies. But it had crossed the heliopause. It had left the region dominated by the solar wind and entered plasma associated with the local interstellar medium. That was a genuine physical frontier. The environment beyond it was subtle. There were no dense clouds of gas. Interstellar space is still an extraordinary vacuum by terrestrial standards. A human exposed there would not feel a wind. Voyager's instruments, however, could detect the difference. Galactic cosmic rays became more abundant. Plasma density increased. The magnetic environment changed in ways that challenged earlier expectations. One particularly interesting result involved the magnetic field direction. Instead of rotating sharply at the heliopause, the field remained more closely aligned with the field inside the boundary than many scientists anticipated. Researchers proposed several explanations. The solar magnetic field might interact with the local interstellar field in complicated ways. The heliopause might possess structures not represented in simpler models. Voyager was providing only one path through an enormous three-dimensional boundary. A single crossing could not reveal its complete shape. This made Voyager 2 increasingly important. The second spacecraft was approaching the heliopause along a very different trajectory. If it also crossed into interstellar space, Scientists could compare the two regions. For several more years, Voyager 2 remained inside the heliosphere. Its instruments detected changes as it travelled through the heliosheath. Most importantly, its plasma science instrument still functioned. That instrument could directly measure the velocity, density, temperature, and pressure of plasma around the spacecraft. Voyager 1 had lost this capability decades earlier. Voyager 2 could therefore provide observations unavailable from its twin. By 2018, the signs of an approaching boundary became stronger. Galactic cosmic rays increased. Particles associated with the heliosphere changed. Scientists watched carefully. The crossing might happen gradually, or it might appear as a relatively sharp transition. On November 5, 2018, Voyager 2 passed through the heliopause. It was roughly 119 astronomical units from the Sun. The second human-made object had entered interstellar space. This time, the functioning plasma instrument gave scientists a direct view of the transition. The solar wind plasma declined dramatically as Voyager crossed the boundary. Measurements from other instruments changed as well. Together, they confirmed that the spacecraft had left the heliosphere. The two crossings revealed something important. Voyager 1 had crossed at about 121 astronomical units. Voyager 2 crossed at roughly 119, yet the termination shock crossings had occurred at more noticeably different distances. These boundaries were not fixed shells. They moved. Solar activity changed the pressure from inside. Conditions in the surrounding interstellar medium affected them from outside. The heliosphere breathed and shifted. Scientists also learned that the heliopause could be surprisingly sharp. Across a relatively limited region, the character of the surrounding plasma changed substantially. Yet influences from both sides could penetrate the boundary. Particles crossed, magnetic fields interacted. The frontier was not an impermeable wall. It behaved more like a dynamic shoreline where two environments met. Voyager 2 also detected an increase in plasma density after entering interstellar space. Voyager observed similar behavior farther along its own path. This suggested that the region just outside the heliopause might be compressed by interaction with the expanding heliosphere. The spacecraft were beginning to reveal how the Sun physically meets the galaxy. For most of human history, the boundary would have been impossible even to imagine. Ancient observers saw the Sun cross the sky. Later, astronomers understood that Earth orbited it. Modern physics revealed the solar wind. Spacecraft measured that wind near Earth and around the planets. Now Voyager had followed it until it ended. The intellectual journey was enormous. The Sun was no longer simply a distant sphere of light. It was a star surrounded by a vast magnetic and particle environment, itself embedded within a larger galactic medium. Humanity could now measure both sides of that interface, and it was doing so with machines built in the 1970s. That fact became increasingly remarkable with each passing year. Voyager 1 and Voyager 2 were now operating in an environment their original designers never expected them to reach while functioning. The spacecraft had been engineered carefully, but nobody could guarantee electronics would survive 4 decades in deep space. Their continued operation depended upon both robust design and constant adaptation. Power remained the central limitation. The radioisotope generators lost capacity every year. Engineers estimated that available electrical power declined by several watts annually. That might sound trivial. On Voyager, a few watts mattered. A scientific instrument might require only a handful of watts. A heater might consume another small amount. Eventually, keeping one system alive could require switching another one off. The mission became a careful negotiation with thermodynamics. Engineers disabled heaters and allowed some equipment to become colder than its original qualified operating limits. To their surprise, instruments often continued functioning. Components designed for one thermal environment tolerated another. Voyager repeatedly operated beyond conservative expectations, but nothing could stop radioactive decay. The plutonium continued weakening. Eventually, the spacecraft would no longer generate enough electricity to operate its scientific instruments. The exact sequence of shutdowns depended upon spacecraft health and engineering choices. Mission teams worked to extend useful science for as long as possible. Communication presented another constraint. By the time both Voyagers entered interstellar space, their signals required many hours to reach Earth. The round-trip communication time approached an entire day. If engineers sent a command, they could not immediately know whether it had worked. They waited for the command to cross billions of kilometers. Then they waited for Voyager's response to travel back. This slow conversation had its own rhythm. A problem might take days to diagnose because each test required another exchange across interstellar distance. Yet the spacecraft continued answering. Voyager 1 became the most distant human-made object. Voyager 2 followed along another path. Neither was heading toward a specific star. They were simply moving through the galaxy according to trajectories created by encounters with the giant planets decades earlier. The gravity assist that once carried them from Jupiter towards Saturn had ultimately determined their interstellar directions. Planetary exploration had become galactic drift, and aboard both spacecraft remained the golden records. They had travelled silently through every encounter. Jupiter's radiation had surrounded them. Saturn's gravity had redirected them. One had passed Titan. The other had crossed Uranus and Neptune. Now both records were moving through interstellar space. The scientific instruments would eventually stop. The transmitters would become silent. But the records required no electricity. Their journey belonged to a timescale much longer than the mission itself. The Voyagers had crossed the heliopause. Their next transformation would be stranger. They would gradually cease being active spacecraft and become artifacts travelling between the stars. By this time, both Voyagers entered interstellar space. Their journey had become almost unrecognizable compared with the mission launched in 1977. The giant planets were decades behind them. Their cameras were silent. The brilliant images of Jupiter, Saturn, Uranus, and Neptune now belonged to history. What remained was quieter. Every day, two aging machines continued moving outward while transmitting measurements toward a planet that had become an unimaginably distant point behind them. For the engineers responsible for Voyager, keeping that conversation alive became one of the most unusual challenges in spaceflight. The spacecraft were never designed for easy repair. There had never been any possibility of sending astronauts to service them. Now even rapid communication was impossible. Voyager 1 was more than 20 billion kilometers from Earth. Voyager 2 followed at a somewhat smaller distance. Radio waves still traveled at the speed of light, but even light needed many hours to cross those distances. A command sent to Voyager 1 could spend most of a day traveling before reaching the spacecraft. Its response required another long journey home. A simple troubleshooting exchange could therefore consume nearly 2 days. If engineers wanted to try several possible solutions, the process could stretch across a week. This changed the psychology of spacecraft operations. There was no button that could be pressed while someone watched for an immediate response. Instead, engineers prepared commands carefully. They transmitted them. Then they waited. The Deep Space Network remained the essential connection. Its enormous antennas listened for signals so weak that ordinary communication systems would never detect them. Voyager's transmitters produced only modest radio power. That signal spread across an expanding region as it travelled toward Earth. By arrival, the energy collected by a ground antenna was extraordinarily small, yet information remained encoded within it. Temperatures, voltages, magnetic fields, particle counts, engineering status. The faint signal still carried the condition of a machine built when much of modern digital technology did not exist. Keeping Voyager alive therefore depended upon two different eras of engineering cooperating across time. The spacecraft remained largely a product of the 1970s. The systems receiving its signal had evolved continuously. Antennas improved. Receivers became more sensitive. Computer processing became vastly more capable. Techniques for extracting information from weak signals advanced. Voyager survived partly because Earth became better at hearing it. The spacecraft itself also required increasingly careful management. Its 3 radioisotope thermoelectric generators continue producing electricity from the heat released by plutonium-238. But radioactive decay never stops. The available power declined steadily. Thermoelectric materials also degraded with age. Every year removed several watts from the spacecraft's electrical budget. On Earth, a few watts might seem insignificant. On Voyager, they could determine whether an instrument survived. Engineers began switching off systems that were no longer essential. Some scientific instruments had already stopped operating because their planetary objectives were complete. The cameras were among the most obvious examples. Others were lost through hardware failures. The surviving instruments were increasingly valuable. because they could measure interstellar space directly. The challenge was keeping enough of them operating while still powering communication, computers, attitude control, and thermal systems. Heaters became important bargaining chips. Spacecraft electronics had originally been designed and tested for particular temperature ranges. Turning off a heater saved electricity but allowed components to become colder. Nobody could guarantee exactly how long an instrument would survive outside its original thermal expectations. Engineers therefore faced uncomfortable choices. They could preserve warmth and lose electrical power needed elsewhere, or they could accept colder temperatures and discover whether Voyager could tolerate them. Again and again, the spacecraft surprised them. Some instruments continued functioning at temperatures well below their original qualification limits. The machines were not indestructible, but decades of conservative engineering margins gave the mission room to improvise. Propellant created another long-term problem. Voyager does not need continuous engine thrust to move through space. Its momentum carries it onward, but it does need small thrusters to control orientation. The high-gain antenna must remain pointed toward Earth accurately enough for communication. If Voyager loses that orientation permanently, its transmitter might continue operating while Earth hears nothing. Attitude control is therefore essential. Small hydrazine thrusters provide the necessary rotations and corrections. Every firing uses a tiny amount of propellant. Over decades, those tiny amounts accumulate. Mission controllers developed methods to reduce unnecessary maneuvers and conserve remaining resources. They also had backup thrusters originally intended for trajectory correction maneuvers during the planetary mission. Those thrusters had been largely dormant for decades. Then engineers considered using them again. For Voyager 1, the trajectory correction maneuver thrusters had not been routinely used since 1980. In 2017, the mission team commanded a test. After 37 years of inactivity, the thrusters responded successfully. The result provided another option for controlling spacecraft orientation. Voyager 2 later underwent a similar transition. It was difficult not to see something almost human in the episode. Although the spacecraft itself possessed no awareness, a component had waited silently for decades. Then a command arrived from Earth. The old hardware awakened and worked. Other problems were less reassuring. Voyager's computers and memory systems were aging. Radiation had accumulated over decades. Electronic components could fail. Individual bits of memory could become corrupted. Telemetry occasionally behaved strangely. Each anomaly required diagnosis using information that might be incomplete. In 2022, Voyager 1 began returning confusing attitude, articulation, and control system data. The spacecraft appeared to remain properly oriented because its signal continued reaching Earth. Yet some telemetry describing its orientation was meaningless. Engineers eventually determined that the data were being routed through a computer that had stopped functioning correctly years earlier. They changed how the information was handled. Normal telemetry returned. The spacecraft had not repaired itself. Humans had simply found another path through its surviving hardware. Then a more serious problem appeared in late 2023. Voyager 1 began transmitting a repeating pattern rather than useful engineering and scientific data. The radio carrier remained detectable. The spacecraft was still there, but its message had become unintelligible. Engineers traced the problem to the flight data subsystem, the computer responsible for packaging scientific and engineering information for transmission. Part of its memory had failed. The damaged region included code required to format Voyager's data. Replacing the computer was impossible. Restarting it could not restore physically damaged memory. The solution had to work around the missing hardware. Engineers examined decades-old documentation and reconstructed how the software was organized. The damaged code could not fit entirely within any single remaining memory region, so the team divided it. Different portions were moved into several available locations. References within the software then had to be adjusted so the separated pieces could still function together. This was programming under conditions almost impossible to reproduce in ordinary computing. The computer was billions of kilometers away. Its memory was tiny. Its architecture belonged to another technological era. Every command required hours to arrive. Every response required hours to return. There was little room for error. In April 2024, meaningful engineering data began returning. Scientific information followed. Voyager 1 was speaking clearly again. The recovery demonstrated why the mission's extraordinary lifespan cannot be attributed only to robust hardware. The The spacecraft had survived because generations of engineers learned how to reinterpret that hardware. Voyager had become less like a finished machine and more like a changing collection of surviving possibilities. When one route failed, another could sometimes be found. When power became scarce, priorities could change. When hardware became colder than expected, engineers could discover whether it continued operating. When memory failed, software could be rearranged. This flexibility had limits. Nothing could replace declining electrical power. Nothing could reverse radioactive decay. Nothing could manufacture additional hydrazine aboard the spacecraft. Every recovery borrowed time. That made the remaining scientific instruments especially precious. Voyager 1 continued measuring magnetic fields, energetic particles, cosmic rays, and plasma waves in interstellar space. Voyager 2 provided complementary measurements along a different trajectory. The two spacecraft were separated by enormous distances, allowing scientists to sample different regions of the local interstellar environment. The plasma surrounding them was extraordinarily thin, yet the instruments could detect subtle variations. Voyager 1's plasma wave system measured increasing electron density as the spacecraft moved farther beyond the heliopause. Rather than entering a perfectly uniform interstellar medium, it encountered changes and disturbances. Some were connected indirectly to solar activity. Even beyond the heliopause, events originating from the Sun could send pressure waves into surrounding interstellar plasma. The Sun's influence did not end neatly at one mathematical surface. Its disturbances could still be detected beyond the boundary. This made the heliopause seem less like a wall and more like a shoreline. The environment changed across it, but the two sides continued interacting. Voyager was measuring that interaction from within the interstellar medium itself. Meanwhile, cosmic rays provided another perspective. These high-energy particles originate from processes throughout the galaxy. Some are accelerated by supernova remnants and other energetic environments. Inside the heliosphere, the solar magnetic field modifies how many can penetrate toward the inner planets. Outside it, Voyager could measure them more directly. The spacecraft that once photographed clouds on Jupiter was now detecting particles connected with events occurring across the Milky Way. The scale of the mission had changed completely. Yet on Earth, the work remained surprisingly intimate. Small teams monitored temperatures. They watched voltage margins. They studied old schematics. They decided which heater could be sacrificed next. There was no single dramatic moment when Voyager became old. Age accumulated gradually. One instrument disappeared, then another heater was disabled. A thruster required replacement by a backup. A memory location became unusable. Each change narrowed the spacecraft's remaining capabilities. Still, the radio signal continued arriving. Eventually, that signal must stop. The available electrical power will fall below what is required to maintain scientific operations. More instruments will be turned off. At some point, communication itself will become impossible. There will probably be no explosion, no spectacular final photograph. Voyager will simply become quieter. One scientific stream will disappear, then another. Eventually, the Deep Space Network may listen and hear nothing identifiable from the spacecraft. But silence will not mean that Voyager has stopped traveling. Its momentum will remain. The Sun's gravity will continue slowing it slightly as it escapes, but not enough to bring it back. The spacecraft will continue into the Milky Way. Its antenna will no longer matter. Its computers will be dead. Its instruments will measure nothing. Yet attached to its body will remain an object that never required electricity in the first place. A gold-colored record will continue traveling through the darkness. And the story of that record begins not with distant aliens, but with a question asked before Voyager ever left Earth. If a spacecraft might survive as an artifact long after its mission ends, what should humanity place on board it long before Voyager crossed into interstellar space? Scientists understood that the Sun's influence could not extend outward in the same form forever. The solar wind had to meet something. Between the stars, matter is sparse, but it is not absent. Thin clouds of atoms and ions occupy the Milky Way alongside dust, magnetic fields, and energetic cosmic rays. The Sun moves through this environment while carrying its own vast bubble of plasma around it. Voyager had finally reached the place where those two environments met. For Voyager 1, the decisive crossing occurred on August 25, 2012. Voyager 2 followed on November 5, 2018. These dates were milestones, but they did not represent the moment the spacecraft escaped the Sun completely. That distinction matters. The heliopause marks the outer boundary of the heliosphere, where the solar wind no longer dominates the surrounding plasma. Solar gravity extends enormously farther. Voyager remained gravitationally influenced by the Sun after crossing the heliopause, just as distant comets remain connected to the solar system across extraordinary distances. Still, something fundamental had changed. For the first time, instruments built on Earth were directly sampling interstellar plasma. Voyager 1 entered this environment without a functioning plasma science instrument. That instrument had failed decades earlier. Scientists therefore had to reconstruct the spacecraft's surroundings using other measurements. The plasma wave instrument became particularly important. It could detect oscillations in the charged particles around Voyager. From the frequency of those oscillations, researchers could estimate electron density. The method transformed invisible vibrations into information about the medium between stars. The first measurements produced a fascinating result. Interstellar space near the heliopause was denser than the plasma Voyager had encountered immediately inside the boundary. This matched the broad expectation that interstellar plasma would differ significantly from the weakened solar wind. But Voyager continued outward. The density did not remain constant. Measurements suggested a gradual increase as Voyager 1 moved farther into interstellar space. This raised new questions about the structure just outside the heliosphere. Perhaps the heliosphere compresses surrounding interstellar plasma as it pushes against it. Perhaps local structures produce variations along Voyager's particular trajectory. The spacecraft was following only one narrow path through an enormous region. Scientists had to be careful about treating local measurements as universal. Voyager 2 offered another path. Its functioning plasma instrument allowed direct measurements as it crossed the heliopause. The spacecraft observed a dramatic decline in solar wind particles around the transition. Beyond the boundary, it entered the denser interstellar plasma. Its observations broadly confirmed Voyager 1's interpretation while revealing differences between the two crossing regions. Those differences mattered. The heliosphere is not a perfect sphere. It exists inside a moving, magnetized interstellar environment. The Sun itself travels through the local interstellar medium. Meanwhile, solar activity changes over an approximately 11-year cycle. The pressure inside the heliosphere therefore varies. The external environment is not perfectly uniform either. The resulting boundary can move, distort, and respond. Voyager was discovering that even the edge of the Sun's domain has weather of a kind. Not weather with rain or clouds. Instead, there are pressure changes, magnetic disturbances, energetic particles, and waves moving through plasma. Some disturbances begin near the Sun. A powerful solar eruption can launch material outward through the heliosphere. Months later, the resulting pressure wave may reach the distant boundary. Eventually, effects can propagate into interstellar plasma beyond it. Voyager 1 has detected such disturbances. This creates an unexpected connection. The spacecraft may be outside the heliosphere, yet the Sun can still influence what its instruments measure. Crossing the heliopause did not place Voyager in a completely isolated galactic environment. The boundary separates different plasma regimes, but interactions continue across it. The magnetic field provided one of the greatest surprises. Before Voyager 1 crossed the heliopause, scientists commonly expected the magnetic field direction to change significantly. Inside the heliosphere, the field is shaped by the Sun and solar wind. Outside, the local interstellar magnetic field should dominate. A noticeable directional change seemed reasonable. Voyager did not observe the expected dramatic rotation. The field became stronger, but its direction remained unexpectedly similar. This created disagreement over whether the spacecraft had truly entered interstellar space. The plasma density evidence eventually made the crossing convincing. The magnetic result remained scientifically interesting. Perhaps the interstellar magnetic field is draped around the heliosphere in a way that produces local alignment. Perhaps the boundary geometry along Voyager's trajectory differs from simplified models. Researchers continue using Voyager measurements alongside data from other missions to refine the picture. This is one reason the spacecraft remains scientifically valuable. They are not merely proving that interstellar space exists. They are testing models of how stars interact with their galactic surroundings. Every star with a stellar wind may create some form of surrounding astrosphere. Studying the heliosphere therefore offers clues about environments around other stars. The Sun becomes a nearby example of a broader astrophysical process. There is another important interstellar measurement: cosmic rays. These are energetic atomic nuclei and other particles travelling through the galaxy. Many originate from violent astrophysical environments, including the remnants of exploded stars. Their exact origins and acceleration mechanisms can be complicated, particularly at the highest energies, inside the heliosphere. The solar wind and magnetic field influence how galactic cosmic rays reach the inner solar system. Outside the heliopause, Voyager can measure a population less modified by this solar shielding. The change was visible during the crossings, as particles associated with the heliosphere declined. Galactic cosmic rays increased. Voyager had moved from an environment shaped strongly by one star into a region more representative of the wider galaxy. You might imagine the transition as leaving a harbour. Near the Sun, everything is dominated by local conditions. Farther outward, the influence weakens. Beyond the heliopause, the surrounding environment belongs increasingly to the galactic sea. Yet the analogy has limits. There is no sudden open ocean. The interstellar medium itself has structure. Our solar system currently travels through a relatively low-density region known as the local interstellar cloud. This cloud is only one component of the complicated material occupying our galactic neighbourhood. Its atoms are incredibly sparse compared with terrestrial gases. A laboratory vacuum on Earth can seem empty, but interstellar space operates on another scale entirely. Even so, Voyager can measure it. Individual particles strike detectors. Plasma oscillations pass through instruments. Magnetic fields exert subtle influences. Information accumulates slowly. This style of science is very different from the planetary encounters. At Jupiter, a single photograph could reveal an erupting volcano. At Neptune, an image could expose a vast atmospheric storm. Interstellar science often requires months or years of measurements. Researchers look for trends. They compare particle populations. They watch densities rise and fall. The drama exists in patterns rather than landscapes. Voyager's increasing distance makes those patterns unique. No functioning spacecraft before it had sampled these locations. There is no nearby replacement. The Pioneer spacecraft also travel outward. But communication with Pioneer 10 ended in 2003, while contact with Pioneer 11 had ended years earlier. New Horizons is escaping the solar system after its exploration of Pluto and Arrokoth, but it remains far inside the heliopause. For now, the Voyagers are humanity's only active instruments operating in interstellar space beyond the heliosphere. Their separation is especially useful. Voyager 1 and Voyager 2 are moving outward in different directions. They cross the heliopause at different locations and different phases of solar activity. Comparing their measurements helps reveal which features might be local and which may characterize the boundary more generally. Still, 2 points are not enough to map an enormous three-dimensional structure completely. Scientists continue debating the global shape of the heliosphere. Older illustrations often showed something resembling a comet, with a rounded nose facing the sun's motion and a long tail stretching behind. More recent models can produce different shapes depending on assumptions about magnetic fields, particle populations, and plasma behavior. Some suggest a more compact structure with complex lobes. Voyager alone cannot settle every detail. Its trajectory samples only narrow corridors. Other spacecraft and remote observations provide complementary evidence. This uncertainty is exactly what makes direct measurements so valuable. Voyager was built before modern heliospheric models existed in their current forms. It carries instruments designed for questions asked in the 1970s. Yet those instruments continue supplying evidence for questions that developed decades later. The spacecraft has outlived the scientific context that created it. That is rare. Most instruments become obsolete because newer technology replaces them. Voyager remains irreplaceable because location matters more than sophistication. A modern detector near Earth cannot directly sample plasma surrounding Voyager 1. It can be thousands of times more sensitive and still be in the wrong place. Voyager's greatest instrument has become its distance. Every year adds hundreds of millions of kilometers to that advantage. Every year also removes electrical power. This creates the central tension of the interstellar mission. Scientifically, the spacecraft becomes more valuable as it travels farther. Engineeringly, it becomes weaker. The radioisotope generators continue fading. Temperatures continue changing. Thrusters age. Computers accumulate faults. Engineers must decide how much power can be removed from supporting systems while preserving scientific measurements. The mission is now a race between distance and decay. Nobody expects the Voyagers to remain active indefinitely. Eventually, electrical generation will fall too low to support the remaining instruments. Scientific systems will be switched off one by one as necessary. Later, the spacecraft may no longer maintain communication with Earth. The final signal might not arrive as a dramatic farewell. There may simply come a day when an expected stream of telemetry fails to appear. Engineers may try commands. The Deep Space Network may listen. Perhaps contact will return temporarily. Eventually it will not. Voyager will become silent. But silence is not the same as disappearance. The spacecraft will still have velocity. There is almost nothing in interstellar space to slow it significantly. Voyager 1 and Voyager 2 will continue orbiting through the Milky Way long after their electronics stop functioning. Tens of thousands of years from now, they will pass through the broad neighborhoods of other stars. They are unlikely to encounter planets. The distances between stars are too large, and their trajectories are not aimed toward known inhabited worlds. But attached to each spacecraft is a deliberate artifact designed for exactly this silent future. It contains no active transmitter. It needs no battery. It does not expect anyone to find it. It simply carries a small collection of sounds and images from Earth. After all the measurements of plasma, cosmic rays, magnetic fields, and distant worlds, Voyager's longest-lived message may be the simplest part of the spacecraft. The golden record is waiting for no one in particular. And that may be precisely why humanity placed it there. In 1977, before either Voyager spacecraft left Earth, a small group of people faced a question unlike almost anything in the history of communication. What could humanity say about itself without knowing who might listen? There was no known recipient. There was no shared language. There was no reason to assume that another intelligence would recognize human symbols, understand human voices, or experience the world through senses resembling our own. There was not even a realistic expectation that anyone would ever find the message. Yet both Voyagers were going somewhere no earlier spacecraft had been deliberately prepared to go. Eventually, they would enter interstellar space. Their electronics would die. Their radio transmitters would become silent. But their physical structures could continue drifting through the galaxy for extraordinarily long periods. That possibility inspired the golden record. The idea had precedents. Pioneer 10 and Pioneer 11, launched earlier in the 1970s, carried small plaques designed by Carl Sagan and Frank Drake. With artwork prepared by Linda Salzman Sagan, the plaques showed human figures and encoded information intended to identify the spacecraft's origin. Voyager offered more room for a message. Instead of a plaque alone, each spacecraft would carry a phonograph record. Carl Sagan chaired the committee responsible for selecting its contents. The group included Frank Drake, Anne Druyan, Timothy Ferris, John Lomberg, and Linda Salzman Sagan, among others. Their task was enormous in concept and tiny in physical scale. They had only one record. Earth contained thousands of cultures, languages, landscapes, species, traditions, and ways of understanding existence. No collection could represent all of them fairly. The team therefore did not attempt a complete portrait. They assembled fragments. The result became a kind of time capsule. Each record was made from copper and coated with gold. A protective aluminum cover shielded it from some of the slow erosion caused by dust and radiation during its immense journey. The cover also carried instructions. If the record were ever found, its discoverers would somehow need to understand that the disk contained encoded information. They would need to determine how quickly it should rotate. They would need to understand how the recorded signals could be reconstructed into sound and images. The designers searched for references that did not depend upon human units. One of the most important involved the hydrogen atom. Hydrogen is the most abundant element in the universe. The record's diagrams used a transition associated with neutral hydrogen as a fundamental reference for time and length, from that physical standard. Other information could theoretically be interpreted. Whether an unknown intelligence would actually understand the diagrams is impossible to know. The attempt itself reveals something about the assumptions behind the project. The designers hoped physics could provide a shared language where culture could not. Another diagram attempted to identify the location of the Sun. It used pulsars. Pulsars are rapidly rotating neutron stars that produce extremely regular pulses of radiation. Their periods differ from one another. By representing the directions and periods of selected pulsars relative to the Sun, the diagram provided something like a galactic address. Because pulsar periods gradually change, the information might even offer clues about when the spacecraft was launched. Again, none of this guaranteed understanding. The record was an experiment in communication across unknown differences. Then came the contents. The golden record contained 115 images encoded in analog form. They attempted to introduce basic mathematics, physical quantities, human anatomy, reproduction, landscapes, animals, plants, architecture, food, transportation, and ordinary human activity. There were images of Earth. There were people working. There were families. There were scientific diagrams. There were views of natural environments. The selection inevitably reflected choices made by a small group during a particular historical moment. No archive of 115 images could summarize an entire planet. That limitation was understood. The goal was closer to offering glimpses. If you had only a few moments to show that Earth was alive, complicated, and inhabited by technological beings, what would you choose? The question becomes difficult almost immediately. A photograph of a city reveals architecture but says little about forests. A human body reveals anatomy but not music. A mathematical diagram may communicate structure but not emotion. Every selection excludes something. The record therefore became less like an encyclopedia and more like a collage. Sound offered another dimension. The record included greetings spoken in 55 languages. Some were ancient languages. Others were spoken by millions of people. The greetings varied in style. Some were formal, some were simple. Together they created a sequence of human voices directed toward an imagined listener beyond Earth. There was also a greeting from the United Nations Secretary-General at the time, Kurt Waldheim. United States President Jimmy Carter contributed a written message. His statement described the record as a gift from a small, distant world. The phrase captured the scale of the project without requiring the spacecraft ever to reach anyone. Earth was indeed becoming small from Voyager's perspective. The record also contained sounds of the planet itself. There was wind. There was thunder. There were waves. Animal sounds appeared. Birds called. Whales vocalized. Human life entered through footsteps, laughter, tools, and other familiar noises. A heartbeat was included. So was the sound of a kiss. These recordings were not scientifically necessary. Voyager could explore Jupiter perfectly well without carrying the sound of surf. That was precisely what made them meaningful. The spacecraft carried evidence not only that humans understood equations, but that they inhabited a sensory world. Earth had weather. It had oceans. It had animals. It had bodies that breathed and hearts that beat. Then there was music. The committee selected pieces from different cultures and historical traditions. Western classical works appeared alongside musical traditions from Asia, Africa, the Americas, and elsewhere. Bach was represented. So was Beethoven. Mozart appeared. Chuck Berry's Johnny B. Goode carried a form of 20th century American rock and roll beyond the planets. There were traditional vocal and instrumental performances from several cultures. No selection could represent Earth's full musical diversity. The committee had limited space. Choices produced disagreement. That was unavoidable. Choosing music for an unknown listener forces an impossible question. What does humanity sound like? There is no single answer. Perhaps the record's greatest strength was that it did not pretend there was one. Its musical sequence moved across traditions rather than declaring a universal human style. Among the record's most personal elements was something invisible to anyone simply looking at its golden surface. During preparation, Anne Druyan had recently become engaged to Carl Sagan. She recorded electrical signals associated with her brain and body for inclusion among the record's encoded information. For about an hour, she thought about ideas ranging from Earth's history to human relationships. The recording could not translate those thoughts directly. Brain signals do not contain a simple readable transcript of consciousness. The gesture was symbolic. A trace of a living human nervous system had been placed among the sounds and images of Earth. The golden record was filled with gestures like this. Some were scientific, some were cultural, some were deeply personal. Together, they revealed as much about the people who created the message as they did about humanity generally. The record was optimistic. It emphasized life, knowledge, culture, nature, and connection. It did not attempt to catalogue every war, injustice, disease, or catastrophe in human history. This choice has sometimes attracted criticism. A hypothetical finder would not receive an objective encyclopedia of humanity, but an objective summary of an entire civilization was never realistically possible. The record was closer to an introduction. Human beings were choosing what they wished to say when given only one brief opportunity. Perhaps that makes the omissions meaningful too. The golden record does not simply show what humanity was. It shows what a group of humans hoped humanity might be remembered for. After the records were attached, the spacecraft launched. Then something curious happened. For the mission itself, the golden records became almost completely irrelevant. They performed no scientific experiments. They supplied no power. They transmitted nothing. During the Jupiter encounters, they simply remained attached. While Eo's volcanoes erupted beneath Voyager's cameras, the record travelled silently beside the instruments. At Saturn it did the same. Voyager 1 carried its copy past Titan. Voyager 2 carried another past Uranus, Miranda, Neptune, and Triton. Neither record needed to do anything. That passivity was part of the design. Their true mission would begin only after the spacecraft's active mission ended. The chances of discovery remain extraordinarily small. Voyager 1 is not travelling toward a nearby planetary system with known inhabitants. Voyager 2 has no destination where anyone is expected to wait. Stars move, the spacecraft move, over tens of thousands of years. Each Voyager will pass through the broad neighbourhood of other stars. Even then, near must be understood astronomically. A passage separated by more than a light year is close by interstellar standards, but hopelessly distant for accidental discovery. Space is overwhelmingly empty. The records may drift through the Milky Way without ever being touched again. Their survival is also not infinite. Microscopic impacts and cosmic radiation will slowly alter exposed spacecraft materials. Over extremely long periods, gravitational encounters with stars and galactic structures will change the trajectories. Nothing physical lasts forever, but compared with ordinary human artifacts, Voyager occupies an extraordinary timescale. Cities can disappear, languages can change beyond recognition, civilizations can rise and fall, continents move, species evolve. The Voyagers may continue circling the galaxy through all of it. Their golden records could remain recognizable long after the civilization that manufactured them has changed beyond anything their creators would understand. This gives the records a strange dual identity. They were ostensibly made for extraterrestrial discoverers, yet their immediate audience was always human. They asked people on Earth to imagine themselves from outside, not as nations, not as competing political systems, not as separate centuries or languages, but as inhabitants of one small planet capable of sending an object into the dark. The pale blue dot photograph would later express a similar idea visually. The golden record had expressed it physically 13 years earlier. Both reduced humanity's enormous internal complexity to something tiny. A pixel, a disk, a spacecraft moving away from home. Voyager's scientific discoveries transformed knowledge of the solar system. Its record performed no comparable experiment, yet it became one of the mission's most enduring symbols because it asked a question science alone could not answer. What should a civilization say about itself when it does not know who will hear? There may never be a reply. The record may never be played. Its grooves may remain silent for billions of years, but Voyager does not require an audience to continue carrying it. The message is already moving, and eventually, when the spacecraft's final electrical systems fall silent, that passive message will become almost everything recognizably human that remains aboard. Voyager will no longer be an operating mission. It will become an artifact. The last chapter of its journey therefore belongs to a future without mission control, without radio contact, and perhaps one day without anyone alive who remembers the launch. The spacecraft will continue anyway. There will probably be no dramatic ending to the Voyager mission. No final landing waits ahead. No ocean will swallow the spacecraft. and no planetary atmosphere will burn them into glowing fragments. Instead, the Voyagers will continue doing what they have done for decades. They will move. Voyager 1 travels outward on one path through the galaxy, while Voyager 2 follows another. Their scientific instruments continue sampling environments no earlier operating spacecraft reached. Their antennas remain directed toward a distant Earth, and their remaining electrical power continues slowly declining. That decline determines the final active years of the mission. The plutonium-238 inside each spacecraft's radioisotope generators has been decaying since before launch. Nothing can reverse that process. Engineers can conserve power. They can turn off heaters. They can retire instruments. They can change operating procedures and make remarkable use of hardware designed half a century ago. But they cannot create new energy aboard Voyager. Eventually, the spacecraft will reach a point where difficult choices become unavoidable. One instrument may have to be switched off so another can continue. Then another system may follow. The exact sequence depends upon spacecraft health, available power, temperatures, and the scientific value of surviving instruments. There is no perfectly predictable final date. Voyager has already demonstrated that hardware can survive beyond conservative expectations. That makes precise forecasts difficult. The spacecraft have repeatedly continued working after reaching conditions their original designers never expected them to experience. Still, physics eventually wins. Electrical production falls. Components age. Propellant becomes scarce. Communication becomes increasingly difficult. At some point, the active scientific mission will end. The final useful measurement might concern cosmic rays. It might describe a magnetic field. It could be a plasma wave observation from the thin interstellar medium. Whatever it is, the last scientific data will begin its journey toward Earth as a faint radio signal. Hours later, antennas on Earth may receive it. Perhaps nobody will immediately know it is the last. Another transmission may be expected. Engineers may wait. They may send commands. They may try alternative configurations. Voyager's history suggests they will make every reasonable attempt to recover contact if something unexpected happens. Sometimes those attempts may work. Eventually one will not. The silence that follows will be unusual because the spacecraft itself will remain intact. A dead Voyager does not stop being Voyager. Its velocity does not depend upon electricity. The gravity assists from Jupiter and Saturn gave Voyager 1 enough speed to escape the Sun permanently. Voyager 2 also follows a solar escape trajectory after its encounters with all 4 giant planets. Their engines do not need to run continuously. There is almost nothing in interstellar space capable of slowing them significantly. They will coast onward. The scale of what follows becomes difficult to imagine. Human history is usually measured in centuries. Geological history uses millions of years. Voyager's silent future belongs increasingly to the second kind of clock. In roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 4 and 45. That sounds close until the distance is considered properly. 1 light-year is nearly 10 trillion kilometers. Even during this relatively close stellar passage, Voyager will remain separated from the star by an enormous gulf. Gliese 445 itself is moving toward the solar system, which helps create the encounter geometry. The spacecraft is not deliberately navigating toward it. There are no engines performing course corrections for a stellar rendezvous. It will simply pass through the broad neighborhood. Voyager 2 has its own future stellar encounters. Tens of thousands of years from now, it will pass within a few light-years of other stars. Again, these are not visits in the ordinary sense. The spacecraft will not enter orbit. It will not photograph planets. Its instruments will almost certainly have been dead for many millennia. It will simply move through changing stellar neighborhoods as the Milky Way evolves around it. The stars themselves are not fixed. Every star orbits through the galaxy. The sun moves. Gli essi sono quelli che muoves. The stars that form familiar constellations slowly change their positions relative to one another. Given enough time, the night sky of Earth would become unrecognizable. Voyager will participate in the same galactic motion. Its trajectory will gradually be influenced by the gravitational field of the Milky Way and by distant stellar encounters. The spacecraft are escaping the solar system. They are not escaping the galaxy. Instead, they will become tiny artificial objects orbiting within the Milky Way. Their journey may continue for billions of years. That timescale changes the meaning of the golden records attached to them. Today, the records are historical artifacts travelling aboard functioning spacecraft. After communication ends, they become the most deliberately human part of otherwise silent machines. The records require no electrical power. Their information is physically encoded, as long as the structures remain sufficiently preserved. Some portion of that information remains recoverable in principle. Whether anyone will ever recover it is another matter. The probability of accidental discovery is extremely small. Interstellar space is too large. Voyager is tiny. Even a technologically advanced civilization would need extraordinary luck or prior knowledge to encounter one of the spacecraft accidentally. The Voyagers may therefore travel forever without an audience. This does not make the golden records meaningless. Their significance was never dependent upon extraterrestrial discovery. They represented a moment when humans understood that their spacecraft might outlive their immediate purpose. A scientific mission had become an opportunity to place something of Earth into a much longer future. That future may look very different from the world of 1977. Consider what has already changed while Voyager has been travelling. The computers used to design and operate the spacecraft belonged to an earlier technological era. The Cold War shaped much of the political world surrounding their launch. Many scientists and engineers involved in the original mission have retired or died. Entire generations have grown up after Voyager left Earth. Meanwhile, the spacecraft continued moving. They crossed Jupiter's orbit. Then Saturn's. One continued to Uranus and Neptune. Both crossed the termination shock. Both eventually passed through the heliopause. Human society changed repeatedly while Voyager followed a nearly uninterrupted physical trajectory. That contrast will only become greater. Thousands of years from now, languages spoken today may have changed beyond recognition. Political borders will almost certainly be different. Coastlines may shift. Human cultures may transform in ways impossible to predict. Voyager will not know. Its dead computers will contain no awareness of history passing behind it. It will simply carry the physical evidence of one moment in civilization. There's another future worth considering. Long before Voyager approaches another star closely, the spacecraft will pass through the distant region associated with the Oort cloud. This immense population of icy bodies is believed to surround the solar system far beyond the planets. Its exact structure and outer boundary remain uncertain, because it has never been observed directly as a complete population. Voyager will not reach its inner regions for centuries. Passing through the full scale of the Oort cloud may require tens of thousands of years. By then, the spacecraft will almost certainly be completely silent. This provides a useful correction to a familiar phrase. Voyager has entered interstellar space beyond the heliopause, but leaving every meaningful part of the solar system is a much longer journey. The Sun's family extends far beyond Neptune. Even after nearly half a century of travel, Voyager has crossed only the beginning of that immense distance. Its achievement is not diminished by this. Instead, the scale becomes more remarkable. Voyager 1 is the most distant human-made object, yet it remains extraordinarily close to home when compared with the distances between stars. Humanity has barely placed a fingertip into interstellar space, and still, that fingertip can communicate. A radio signal leaves Earth. It travels past the Moon in little more than a second. Minutes later, it passes the orbit of Mars. Hours later, it reaches the region where Voyager continues outward. A small antenna receives the command. Electronics built in the 1970s interpret it. Later, a response begins travelling home. That exchange may be Voyager's most extraordinary achievement. Not the distance alone, not longevity alone, but continuity. The same machines that photographed Jupiter in 1979 later measured interstellar space. They connect two eras of human understanding. When Voyager launched, scientists had never seen active volcanoes beyond Earth. They had never visited Uranus or Neptune. They did not know the detailed structures of Saturn's rings. Europa's possible ocean was not yet the compelling target it would become. The heliopause had never been crossed. Voyager helped change all of those perspectives. Its discoveries also changed the missions that followed. Galileo returned to Jupiter and examined its moons in greater detail. Cassini spent years orbiting Saturn and revealed Titan and Enceladus as astonishingly complex worlds. New horizons crossed the outer solar system toward Pluto. Modern observatories study planetary systems around other stars. The questions expanded because earlier spacecraft showed how much remained unknown. Voyager's influence therefore continues even after its planetary encounters ended. Every unexpected landscape taught scientists to be cautious about assuming distant worlds were simple. Io showed that a small moon could be violently volcanic. Europa suggested that an icy surface might hide a deeper story. Titan demonstrated the complexity possible inside a cold atmosphere rich in organic chemistry. Miranda revealed a geological history that remains difficult to reconstruct. Triton showed activity at the edge of the planetary system. The heliopause itself refused to behave exactly as simplified expectations suggested. Again and again, Voyager encountered complexity. Perhaps that is the most consistent lesson of the mission. The farther humanity looked, the less empty the solar system became. The outer planets were not merely large spheres. They were systems. Their moons possessed histories. Their rings evolved. Their magnetic fields created invisible environments. Gravity transferred energy. Atmospheres moved. Frozen surfaces changed. And beyond them, even apparently empty interstellar space contained plasma, magnetic fields, cosmic rays, and echoes of solar activity. The universe did not become simpler with distance. It became richer. One day, Voyager's radio will disappear into the background noise. The Deep Space Network will no longer receive meaningful telemetry. The mission logs will close, but somewhere beyond the planets. The spacecraft will continue along trajectories determined decades earlier. No human hand will guide them. No command will arrive. They will carry the marks of their construction, their instruments, their antennas, and two golden records made on a small planet around an ordinary star. For billions of years, they may circle the galaxy. They may never be found. They may never need to be. They have already completed the most important part of their journey. They carried human curiosity farther than anyone in 1977 could confidently promise. And for a brief period in cosmic history, Earth was able to listen as they entered the space between the stars. The signal will fade. The journey will not. The Voyagers will simply continue into the dark. And back on Earth, beneath the same night sky that once inspired people to wonder what those distant, wandering lights might be, their story will remain. A reminder that exploration often begins with a question. Then a machine is built. A signal is sent. And somewhere far beyond the familiar sky, an answer quietly returns. The radio grows softer now. The planets are far behind. Jupiter becomes only another distant point near the Sun. Saturn's rings can no longer be seen, and Neptune has disappeared into the immense darkness. There is nothing ahead that Voyager needs to reach. No appointment remains. No countdown is running. The spacecraft simply drifts beneath the ancient stars, carrying a small memory of oceans, wind, voices, music, and the world where its journey began. For a little while longer, Earth listens. Then someday silence. And still Voyager travels.